Okay, so good morning, everybody. It is our pleasure today to welcome Irena Hajnsek, who's professor at ETH Zürich, and she's also very much involved with the DLR in Munich. And Irena is a specialist of pulsar, Polinsar, Poltomosar, all these all these derivations of that use the polarimetric diversity. And today she will present you some advanced applications of which use polarimetric diversity to improve the estimation of geophysical parameters.
Okay. Yeah, thanks a lot, Laurent, for this introduction. Yeah, everything is a very good mix to characterize what I'm doing. So I'm originally was coming from DLR, from the German Aerospace Center, where I was doing also my PhD on soil moisture estimation using prometric SAR, and was developing a model how to estimate soil moisture. But now today, you see, we have a different topic. It's ice and snow, so that's it changed a little bit. But during the years, I've done quite a lot of different things. So a lot of things related to the techniques that we use in polarimetry and interferometry, and also the combination Pol-INSAR. And as Laurent was also saying, we also recently use more and more tomography. Yeah, as you have already heard about it a little bit yesterday, we have already the combination Pol-INSAR for forest height inversion. So that's one of the main applications that is also running at DLR. But in addition, I'm a professor at ETH Zürich in the environmental engineering department or institute. And here I'm mainly teaching Earth observation. And I have on both sides a research group with a lot of students. And some of the students will also be next week here, and we'll present some results at Pol-INSAR. Yeah, so there's a little bit about myself. So what I'm doing mainly is using these techniques in order to employ it on different topics, not only agriculture, soil moisture, forest, but also a lot of things in cryosphere. So that's our main part that we are doing. And what we're using is not only the technique, we try also to use electromagnetic models in order to invert also parameters. So that's a little bit the main part that we are doing. Yeah, I thought I start with to introduce the topic snow height estimation, because this was a little bit of a surprise, I know, because in the program there was not standing what will come as a application, and it will be surprised what Armando Marino will do. So I also don't know. So it's a little bit surprise. So I decided snow height estimation to go through this main topic, and I was also deciding not to switch to a lot of different other applications, but really stick to one, and then also to do the exercises on this one. I thought that's probably much more convenient as for the mixture. Yeah, and I thought I could introduce it it is very hot nowadays here, and you experience heat in Toulouse. At least we have experienced a lot of heat in Germany, where I'm just coming from now, but I just heard that last 2 days was a completely rain event here. So it was raining nonstop. So it's probably not the real introduction to it from the heat point of view. Yeah, so I think snow height estimation is still an important parameter. It's not only it's one of the parameters that we do in the cryosphere applications. And I will introduce it a little bit more, what we are doing here. Okay, let us just start then. So my talk today will be a little bit why SAR is good for snow parameter estimation, and then introduce the parameter that we will use also later on in the practical, which is the coil-pol phase difference, the CPD. I will introduce data that we will also use. So these are the tandem X data from the German aerospace satellite, which is mainly a copol system. So it has also capability to do fully parametric data acquisition, but only experimental. And experimental means it's only in certain phases we have launched it. Up to now, we had only 2 phases where we really used it, which means a very limited time. So from this point of view, it is really more a copol system. And therefore, I will also introduce how we can change from quad pole, because most of the things you have heard probably this week is what you can do with fully parametric data. And most of the satellites still today do not have really fully parametric data. And my intention here is to go a little bit back and to see what can you also do using dual pol. I think that's probably also important for you, specifically if you like to use also other kind of systems. And then I will also introduce a propagation model and how to estimate snow height. So that's in principle the main structure that I have for today. And kind of these, I will also go through the exercises then, which I will introduce then in the afternoon. Okay, let us start with the image that you see here. I mean, you have seen already a lot of SAR images and probably a lot of different parts of SAR images. Probably this window, we can close it probably even more. That's better. Okay, good. Yeah, my question would be first, what do you see here? Do you have an idea what this SAR image is about? It's looks very, let me say, yeah, very heterogeneous, has a lot of different features on it. But what do you think what we see here? You can just scream in whatever you like. Sorry? Montagne, yes, right. Yeah, it's a kind of yeah, it's mountains, right? Mm-hmm. Yeah. Sorry? Glacier, yes, it's a glacier. Where is the glacier? Is this the glacier here? Sorry, I need to open it. The glacier is this one, right? Here, this one, this kind of flow. It has a specific shape. This one. Can you see in principle on the color? What does the color means here a little bit? The grayish and the different grayish colors. What do you think? And what is this one? What could be this one here? Yes, yeah. So in principle, it's our geometrical effects that we have in SAR because we are side looking, right? And what you have is these kind of geometrical, yeah, let me say, features that you have, which is in principle, it means either we have foreshortening, this is one thing, we have layover, specifically very strongly on very, very high mountains, right? This is what we have normally. And why is this very bright then? And why these areas are very dark? Why is this bright and this dark? Shadow, yes, this is shadow, yeah, but it's not completely dark, right? If it would be completely dark, black, then I would say, yeah, it's very typical, completely shadow, and you get no information back, right? But what could be this too? We get a little bit information back, right? We have some structure here. And what is the difference between this area and this area? If it's mountain, so what do we see here? Where are the peaks and where are the valleys, right? This is the question here. Which is a peak and which is a valley? Do you have an idea? Somebody? This one is a valley, yeah, or the negative slope, right, of a mountain, right? And this is a kind of peak, is a positive, let me say, towards the satellite, right? And like this, you can identify from where the satellite was flying. So from where was the satellite flying now? Yes, from this side, right? Yeah, right, yeah. So the satellite was flying here. From this side, it was illuminating in this area. And then we see the peaks here are kind of overlaid or more closer. I mean, the peak is closer to the sensor. So therefore, what you have normally is a foreshortening. So the signal is shorter. And everything that is negative, so on the other side of the mountain, it's a little bit stretched, as you can see here, very strong stretched on, and you get less information back, right? Because the whole energy is really coming from the peaks of the mountain here towards the satellite. And then what we see very well here in this case is still this flat areas, which we can see here very well on the glacier itself. So the glacier has also some structure. Do you see the structures? What kind of structure do we see on the glacier? I have two features that I like to point out. Here, this one. Yeah, so what could this be? Crevasses, right? Yes, yeah, these are crevasses, right? Yeah, sure. So these are crevasses, and you see it very, very strongly here, right? So which means this part probably is a kind of an area which is higher located, because this seems that the crevasses are going some kind of down, and therefore you have this kind of breaking up of the ice masses going down to this channel or coming together to this place. So this place is called Concordia Place, where all the different glaciers, so this one, these and these were coming together and then floating down the valley. And here's the lowest part actually of the valley. And here we have the highest parts of the mountains. Yeah, this is one thing. And then the second feature that I like to hear from you, which is also very typical for glaciers that you can see. Another feature that you think? Probably not so dominant, but still you see it. Yes. Oh, sorry. No, just the lines. Yes, right. So that's very typical, right? The lines are very typical. Here you see the lines. So these are the lines floating down the glacier, so that you see also some lines. See a little bit less here, right? But here there are some lines which are floating down. Yeah. So that's yes. Oh, okay. This is a point which we will go now through it. Yes, a very good point. So why glaciers sometimes dark and sometimes very bright, right? It has something to do with the material and the interaction of the electromagnetic wave with the snow and the ice. And we will go through it. Yes. So what do you think? Would this be bright or dark more? What is your feeling? This is a bright one, right? You will say, okay, good, great. Yes, so yeah, that's a bright one. And we will go through it, what the reason is for this kind of difference. But before we do this, I think sorry, it doesn't work. I need to go here always, sorry. Okay, I would like to just introduce a little bit why we use radar techniques for snow, for what this is really good. I mean, we have also in remote sensing, we have also optical satellites, right, which can also estimate snow. So that's also possible. But why and what is better, let me say, using a microwave? And the one thing is, and this has also something to do why we see it bright or dark, is in principle the penetration capability of microwave sensors into snow. So what does it mean? So in the higher frequency range that we have, which is around, let me say, yeah, can be in P-band with wavelengths of around 80 centimeter until, let me say, X-band, which is a usual distribution of wavelengths that we have. So P, L, C, S, C, and X-band. So these are the wavelengths that we use, and these are all in the range that you see here, for example, in this frequency range between, I don't know, around 800 or 600 megahertz until here 50 gigahertz. So this is the frequency range we have. And this means we have wavelengths from around 80 centimeter to 1 centimeter or even a little bit less. And depending on the wavelengths that we have different penetration capability into the snow and into ice. Why we have this? Because snow and ice is has a very low dielectric constant, which means very, very low moisture in it. It's a very dry media, kind of dry media. So therefore we have this stronger penetration capability. However, there's a note, if you go to very, very high frequencies, for example, around already, I would say, yeah, from 12 to 50 gigahertz, and you need also to take a caution about the atmosphere, because here we get already much more atmospheric influences. Yes, so what is typical interaction of microwave and snow and ice? So normally what we say in terms of penetration capability, so if you have high temperature, which also means when we have high temperature, you have also a melting on the surface, so of the snow or ice, depending what you have. And if you have high temperature, normally the penetration capability is very, very low, right? So you have no penetration capability, and all the penetration, you have, which means you have no penetration. All the scattering, what you have, is in principle scattered away from this surface. We call it kind of surface scattering. For total reflection at this, for total reflection of the surface, this is actually when I say we have high temperature, which means above 0 degrees. So if you have a lot of, let me say, very, very dry surface, then we could also have total penetration, which means so the temperature must be much, much more below 0. And in this case, also the wavelength needs to be a little bit longer, which means you go to lower frequencies. And then for volume scattering, this is also what you have normally. So you penetrate, you interact in the volume. So your electromagnetic wave is interacting with the different crystals and grains that you have in the volume. And like this is some kind of below 0, right? So it starts off below 0 and can be, yeah, until minus 30 around. So everything that's below 0 is already good. And you get already kind of volume scattering. And for these frequencies here, we are considering smaller than, or let me say higher than, smaller than 5 gigahertz, because there we have the longer wavelengths. And we would need also to have a specific amount of depths, of snow depths, in order to penetrate and to get volume, right? If you don't have enough snow, you would also not get enough volume scattering. Yesterday you have seen, so we have a lot of volume scattering in forests, right? Because forest is high. You have kind of forests of 30 meters, and we are talking here about 2 meters for snow, right? So it's a big difference in how much volume scattering you would get, really. There's a model that has been developed by Roth et al. He was here taking a principle, the sigma 0, which means the radar backscattering intensity, in order to estimate or to model how the propagation of the wave is in this media, air, snow, and ground. So these are the 3 main parameters. And he was in principle getting a sum of these of the sigma 0, which we call the radar backscattering intensity, of all of these different contributions that you have. So the one contribution is the interface between the snow and the air. So this atmospheric interface, and then you have also the interface or the scattering contribution that is coming back from the volume. So sigma volume. Then you have an interaction ground and volume. So the ground and volume, or you have an interaction only on the ground if you do total penetration. This is a little bit what we said here. So you could have total penetration. So if you at least consider the volume as a snow volume, then you can have either, let me say, depending on the temperature, only interaction here on the snow surface, or you have volume scattering here, interaction with the crystals, and depending on the grain size of the crystals, of the snow crystals here in the volume itself. Or if you have really completely penetration, you get only kind of information from the ground. So also depending on the size of the volume. So as said, would be good to have kind of more than 2 meters for sure. You also, let me say, you can get already, if you go high frequency, you can get also volume scattering from 1 meter snowpack. So that's also possible. Yeah, that's a little bit what is done. What we have also is a lot of interferometry already ongoing, but as said, so I will today more focus on polarimetry. However, I like to just to mention what also in polarimetry is done. For example, what you can do, you can have the interferometry in repeat pass, which we call also multipass coherence. And what happens here, if you have in repeat pass, so normally the satellites have a certain repeat pass time. Do you know what are the repeat pass times of satellites? Sentinel, for example. It is how much? 6 days. Yeah, if you would have 2 satellites in the moment, we have how much? 12 days. Okay. So imagine you have one acquisition, day 0, right? And then after 12 days, again, an acquisition. What do you think what can happen with the signal? If you like to do interferometry, and interferometry, you have heard already a lot about it. Sorry? I heard something here, just louder. you could have temporal decorrelation. And with this means you have no signal anymore, right? So you cannot use the phase information, for example. And this is meant here. So multipass coherence decay means because of if you have in between this acquisition, a lot of snowfall or kind of changes, metamorphism ongoing in the snowpack, it means that you would not get anymore any kind of very well good results. So what you would need is a high frequent sampling. Then it would be good, right? If you would have every day a sample would be perfect. So then multipass can be used. But normally today, we are a little bit limited still, but hopefully in future we will have a higher frequency, let me say, in acquisitions. And then what we could also do in using interferometry is using single pass systems. Yeah, here we can do too. And then in this case, it would be what we could do is we could generate a digital elevation model, right? With one single pass system. Single pass system means I have two acquisitions at the same time, right? There's one satellite mission, which I will later on also introduce, which is Tandem X, which is able to do this. And like this, you can get the coherence on the same spot of the time, which is good. So you have a high coherence then because it's instantly taken. And you can do the change, let me say, sorry, you can do the change of the digital elevation model. So you make of the single pass interferometry one acquisition, then over a time, in this case, it's after 11 days, you can do the second one, and you can compare in principle these different digital elevation models in order to see what is the snow height estimation. So that's in principle also possible to be done. What is also possible is to using differential cell interferometry, which is in principle also good to use, but we have also if you use just DE-INSA and not multipass, the problem here is often also that we have frozen ground. And the problem is with frozen ground, if you do DE-INSA, that you cannot distinguish I'm now below my surface because frozen ground means I can penetrate also in the ground. And so my snow height, it's getting more wrong, right? Because I'm getting more volume because I can penetrate into the ground. So that's a little bit for the snow observation, a little bit a problem here. So frozen ground can be also that you get some additional scatterers. So that's a problem. Here we have the same problem with the snowfall that you can also have kind of complex path delays and for sure also associate atmospheric relations. So therefore today what we will do, I will focus on one single set using just one acquisition and compare this acquisition in time. So this is what we can do using this polarimetric phase difference, which is called copol phase difference. And I will introduce now what the copol phase difference is. Oh yes, probably just to say, so one of the first people which were working on this concept of the copol phase difference is actually Giuseppe Parella, who's now also at ESA working. He was doing a PhD at DLR, and Sylvan Lyons, who is now working also in a company, and he was doing also a PhD on this topic at ETH. Okay, let us go. What is a copol phase difference? So most of the things you have already seen, so therefore it's quite simple for you today. It's a very relaxing day, not so much equations as you have seen on the last days, which probably it's relaxed you too and your brain a little bit. Okay, what you see here is a Sinclair matrix. So this is very easy now for you, right? Where we have all the four elements, how we acquire data. We acquire data sending an H component with the antenna, sending it to the ground, and we receive also then the H component. So therefore we have these four elements here, which is everything with transmit and receive. And out of this, we can build up a lexicographical scattering vector. You have also heard there's different ones, which is called also the Pauli scattering vectors, but I'm focusing here now on the lexicographical scattering vectors, which in principle, out of these, we use three elements. Why? Because we know already that HV and VH in a monostatic case is theoretically the same. So we have here the reciprocity theorem, and mathematically, this is really the same. So therefore, we can average it. And therefore, we have only, it's reduced by 3 elements and not 4 elements. For the bistatic case, this would be different. So if you go next week also to PolINSA, you will see also some bistatic let me say, talks. And here you will see that these two elements are differently if you go to the bistatic. Bistatic means only that the transmission of the system and reception of the system are separated spatially. So they are not on the same platform. And therefore, you get an angle between transmission and reception. And if you have this angle between reception and transmission, you get here differences due to the different viewing angles in the VH and HV. Okay, so that's still very simple. And then out of these, using now this lexicographical scattering vector, we can build an outer product. This you have heard too already. And we can derive the covariance matrix. So this is something that you have heard also in the course. We have, if you take now the Pauli scattering vector, you can get also the coherency matrix, yes. But I'm stopping here with the covariance matrix. And then the covariance matrix itself is also easy now for you. We know we have 3 by 3 elements. And this is by definition a positive semi-definite matrix that you see here, where we have in principle mainly positive eigenvalues if we do the eigenvalue and eigenvector decomposition here. So the main important elements here are the diagonals, which are these ones, and you see this intensity, so nothing else as elements or parts of the scattering vector that you see here. But what we get in addition, and this is important for us now today, is we get these relations. We get relation between the HH channel, the cross-pole channel, and the VV channel. So these are the relations that we have here. And the relation in principle provide us a view on how strong are these two elements correlated to each other. And if I know how strong they are correlated, I know how strong my polarization diversity is. So in principle, these elements tells me a little bit about the correlation between these other elements, and this provides me a view on how strong my object on the ground that I measure is polarized. So that's a little bit a view on how we see this covariance matrix. And for the copole phase difference, it is nothing else as taking in principle one of these channels. Copole means really not the cross pole, but the copole, so the HH and VV. And we are looking in principle here only on the phase. So the phase estimate in principle, so the CPT is nothing else as a phase of the relation between HH and VV here in this arctangent display. So what does it mean? In principle, these elements, I said already that the diagonals are intensities. We see it with the square. And these elements are complex values. So we have a phase information and we have also the intensity, so the strength, the signal strength. So one is the signal strength and the other one is a relation, the phase relation between these two polarization that we have. So therefore it's quite easy today. We are just looking in principle on one of these elements and not on the intensity, but only, let me say, on the phase, so the polarimetric variation between HH and VV polarization. I just like to distinguish this. I think this slide you have seen already yesterday from Matteo, just to distinguish what are the coherences, because with the HH-VV phase, we can also build up, or we can normalize it, we can also build up a coherence, an HH-VV coherence, which is then, for our case, only the polarimetric coherence, so which means the relative differences between these channels that we have, right? So there's a relative difference. For interferometry, what we see, that's in principle the difference between two acquisitions. So this is done by one acquisition and one spot. And this is really by two acquisitions. And here we have the distances to the ground inside. So that's our differences of the path length, let me say, that we have. So these are our interferometric coherences. And then the Pol-INSA, you heard yesterday, is in principle a combination of using these polarimetric channels with, in principle, two acquisitions that we have. So that's a difference. But today, as said, right, I need to go always back. We will just focus on this first part. So we were looking also, or we will look on polarimetric coherences. Okay, let us introduce now the Tandem X mission, which is in principle a mission with two satellites. The one satellite is TerraSyrix, which is this one here. This one has been launched in 2007, so as a first satellite, and in 2010, we had the launch of the second one, which both are very identical, completely identical satellites, which has been launched. And then since 2000, let me say 11, we have now the acquisition of single pass interferometry, which means we have an acquisition of the same region here illuminated by these two satellites. Probably I need to mention, because I was saying before, so the satellite has different modes. So we can do kind of monostatic acquisition. This means that only one satellite can transmit and receive, and separately these two can transmit and receive. But most of the time what we are doing and operating here is a bistatic mode. This is what I was mentioning before, which means the one is transmitting and the other one is receiving. So that's in principle the main part. Why we are doing this in order, because if you have here transmission and reception separately, and you see you have a certain distance here, this means also you have a time in between, even though these are only a few seconds, you can still have temporal decorrelation. This system is working in X-band, which is around 3 centimeter wavelengths. And in this case, could be severe, specifically in tropical forest, a little bit what you have heard yesterday on forest, because the forest leaves and everything is moving. So if you have a storm ongoing, you could have temporal decorrelation ongoing, even in seconds, as said. So therefore, this mission has been really constructed like this, that you have a bistatic acquisition who has really instantly without any time delay acquisition from the same region. Why we are doing this? Because this mission has been constructed to do a global digital elevation model. And this is what has been done since years. So the global digital elevation model has been already acquired and is available since 2015 in the spatial resolution of 12 meters around, spatial resolution, and the vertical accuracy up to 2 meters or 1 meter even for flat terrain. So this was the main idea. And so this is also why it is a single pass system. However, it is not only for digital elevation model can be used, right? Can be used for a lot of different other applications, and that makes it very interesting. You see it already. Oh yeah, these are the interferometric. So the bistatic single pass interferometry sync that you see is right here. Oh, sorry. I'm always thinking I can do this with my pointer. I need to be closer here. So what you can do in addition, for sure you can do digital elevation models using single pass interferometry, but you can also go in different other passes. So the thing is, what you get is synthetic aperture radar data, that's clear. And if you go in this direction, you can get these sigma 0, so the radar backscattering intensities, if you like. And this is available in single, dual, and as said, experimentally also in quad-pole polarization. As said today, most of the time we use it for dual pole. The digital elevation model that has been constructed globally was done in a single pole in HH polarization. So if you are interested in digital elevation model, then you can also take these. This is just that you know it's in single pole. Okay, and then what you can do on the other side, you can also use the complex data here. And you know, we're transmitting and receiving it from two it's always 11 days later. Then you can also do this multi-pass interferometry. So the single pass interferometry, we have done the DEMS, or you can construct DEMS. And with the multi-pass, you can also do, either you can do differential sound interferometry in order to detect changes or any kind of other things that you would like to do. Okay, and if you go here up from the complex data, you can also do here the parametric phase differences. The thing that I was just introducing now is in principle looking for phase differences in the dual pole polarization. And this is the things or the main measurable or observable that we would like to use today. Okay, how is this acquired? Like just a small excursion before we go to the height estimation. Is in principle, we have the transmission and reception. This is always what we do. So for single polarization, it's clear we transmit an H polarization and we receive then also the H polarization. So that's quite simple. For the dual pole, it's like normally like though you transmit the H polarization and you receive then V and H. So that's in principle the difference. And for the quad polarization, it's clear you transmit H and you receive H and V, and then you transmit in the second pulse again V and you receive H and V. And like this, you can build up your scattering matrix. And this is also how Tandem X is working, or TerraStar X, the two mission. However, we are focusing today on this dual pole, and why I'm saying this, probably I need also to mention there's a difference to Sentinel, because probably you will use Sentinel data later on. So these are acquisitions which are coherent acquisitions. Probably need to mention this, coherent acquisitions, which means we preserve also the core parametric phase that we have, right? In this HH and VV. You have also, I think, phases in Sentinel. So, but the problem, and this is what we will see now, is what can you do with cross-pole phases? Because you have not the opportunity to have HH and VV phases, as I suggest here, but you have only the opportunity to have a co-pole and a cross-pole. And the question is, what kind of information content do I have if I have a co and a cross-pole? And I'd just like to show this here now in the next. However, before we do this, just also a caution of note that needs to be taken. So what is the price to be paid if I go from a single polarization to, for example, quad pole or even dual pole? So this is a constellation, how it works when you have an acquisition scenario. So let's consider that this is the source width that we have, right? Our scene on the ground, we have a satellite. The satellite is transmitting the signal here now, let me say in H, right? A single pole transmitting. And then until he's transmitting the next pulse here with a chirp, what is happening? So he's transmitting, and in principle, he's receiving the signal back, which is the red part. So there's a reception back to the sensor, depending, let me say, on the time that you have until you send the next one. So if the next one is again transmitted, then there is a switch and the reception part is closed. So you have only here a limited time in order to receive this. And therefore your source width is limited to the time of this transmit and reception. This is also called, this time here is also called 1 over PRF. PRF is the pulse repetition frequency that you have. So the repetition of the frequency repetition of this pulse. Okay, if you go again back to what is quad pole, we said already, if you have a monostatic case, then we have a transmitter and receiver here. And when we transmit H and receive V and H, and then within the same PRF, let me say, we are also transmitting the V and receiving V and H. How we build up now our scattering matrix here. So this is our transmitter. What we get a vector which has in principle here the HH element inside. You see the HH element, and then receive H and V. So it means we get this two-dimensional vector. And out of this two-dimensional vector, in principle, what we build up is these two parts here. So we build up the HH and the VH parameter here because we have H and V. And if we transmit the V, we have the transmission of V, but we receive H and V. And in this case, what we get is the HV and VH polarization. Okay, but what happens now when I'm going, let me say, from a single pole to a dual or quad pole, and because of this PRF here, so for a single pole, again, the PRF is quite long, can be quite long, but as I need now to transmit H or H and V here, what is happening, this time of the acquisition time is reduced. And what is happening with the source then as a result is the source is in principle shrinking down. So you have in principle a smaller source width in this case because of these time constraint that you have actually for the reception and transmission. So just to say that this is also important if you now have a look on this. Okay, and for a dual pole again, so as said, so you have a little bit constraint on this PRF, so therefore it's reduced. And if you go for dual pole, it's nothing else. So you have an H, you transmit an H, you receive in principle H and V. So you get these components, and then you again transmit a V, you get H and V, and you receive these kind of part, which are a little bit separate because you have a separated PRF constellation, once in H and once in VV. So I'm just like to go now a little bit into polarimetry to explain you, and this is what I was saying before, to say you can also do all this polarimetric stuff that you have done or have seen now during the whole week, where you use fully polarimetric scattering matrices and you derive your entropy and alpha constellations, or even the coherences between the different polarimetric channels. And this is what I was saying before. Let us check a little bit what kind of information content we have if we use not only HH, so the copole, but co and cross, for example. It looks a little bit complex, but it's quite easy. What you see here, again, a lot of formulation, but it's not so difficult because you know most of the things already. So here, this is a traditional covariance matrix that you have with the 3x3 elements that you have seen before. And now we reduce it to a 2x2 because we have only 2 elements now, right? Because we are dual pole. And if you're dual pole, we construct a dual, let me say, a scattering vector with 2 elements. And this you see here can be HH and VV, but can be also HH and HV, so co-cross, could be any kind of combination. So, and if you do an outer product of it, then you can also build up a smaller scattering matrix, right? Which has a 2-dimension, not a 3-dimensional one, because you have only 2 elements. So you can get also in principle the intensities here of A and B, and you can get here the correlation between A and B, right? These elements are the correlation between both. Okay, and if we have now here different cases, how you can build these up with this A and B. In case 1, you can transmit, let me say, H. This is what we have seen before. And in principle, you get then these 2 elements here in the scattering matrix. Okay, and if you transmit, let me say, V, you in principle are also getting 2 elements. I will explain why later on. And if you go H and V, then you in principle get these 2 elements here. Okay, and these are now the pictures out of it, using these different cases. So you have one case where I have now the combination HH and HV, right? This is the co-cross, the thing that we would like to see. So let us consider this is just a normal image where you have a little bit agriculture and forest areas, and you have some surfaces here, probably also some lakes. And here you have an urban area. And this is a very typical natural scene that you probably see thousands of times when you use, in principle, Pauli scattering vector. So that's derived with the Pauli scattering vector here with the typical colors that you have. Blue is in principle surface scattering, red is a dihedral scattering, and green is a volume scattering. Okay, and if you go now to this combination that I've said, just 2 of them, this what you see here is a coherence. I was already introducing the coherence. In principle, it means it's only normalized. So you have a normalization between HH and the cross pole here. So therefore, this normalization. And you see already, it is very noisy, right? It's really dark, and we can't really see the structure that you see in the real scene. The same as if you take now VV and the cross polarized term here, right? Also here, it's very, very dark. When you look now to this copole phase that I was mentioning before, the HH and the VV, you see it here very well. So you see the coherence. Do you remember the coherence tells you the similarity also between 2 images? And here in this case, it means where I have very, very high coherence, so high values means HH and VV are very similar to each other, right? So here I have very strong similarity between HH and VV, and they get some information content, because if I have very low here, that's very low, dark is very low, very low relation between these 2 channels, between HH and VV, it's very low. And this means I have a lot of noise, right? If I have a lot of noise, I can't really use this information content. That's a little bit a problem. So it's good to have high coherence, not only in interferometry, but also in polarimetry. It is good because then you can use this for any kind of classification or any kind of other things that you would like to do. Just to say, so the parameter is important to have high coherences. Otherwise, you have noise effects and you can't use it. And you see now just on this typical scene, if I would use snow, actually, it would be completely decorrelated, it would be completely black. So it would be only noisy like you see here. So therefore, I was using a natural scene so that you see a little bit of difference. However, there are some points, and you see some of the things here which are bright. What are these kind of features? What can this be? So there are some things which are high coherence still in the image. No? I'm telling it's completely decorrelated. You see most of the parts, yes, but there are some features which are really bright. Yeah, so it's man-made structures, buildings, whatever, streets, light poles, can be everything. And you see it here very well, right? These are kind of, looks like really buildings here. And here too. I don't know what this is here, these parts. Yeah. And here it's also mainly buildings, what you see, right? There's also very high coherence. So if you look for man-made structures, which is not changing, yes, you can use also these kind of information content, right? I think that's fine. But if you like to look for natural areas, which we call sometimes distributed areas, then this one would be more preferable to be used in order to get some information, because here you have a coherence information which is behind. Okay, so that's in principle why we have here no correlation, right? So this is what I'm saying. So in principle, the information content for distributed areas is here really zero. So therefore, these cannot be used. So what you do in principle, if you build up this matrix, you have anyway only these two elements. So you cannot do a correlation between them because the information content for distributed areas is very, very low. Whereas when you use the copol phases, you can use this correlation coefficients here, the correlation between HH and VV in order to get more information content. You can also still use these ones separately, yes, but what is missing is here for distributed areas, right? The kind of correlation factor that would bring you to the next level of information content. So just to say why it's good to have also copol and what kind of information content you get if you get co and cross. Okay, going now a little bit, again, reducing the dimensionality from 3-dimensional to 2-dimensional. You have heard this already too. So that's now the coherency matrix with the Pauli scattering vectors. So what you can do is this diagonalization, where you can retrieve the eigenvalue and also the eigenvectors. This is something that you have heard already on Monday, if I'm sure, or on Tuesday, I'm not sure when the Polarimetry session was. And what you can build up out of these are in principle from this eigenvector and the eigenvalues, you can build up kind of statistical parameters. And the statistical parameters are entropy, anisotropy, and the alpha angle. So this is what you can do traditionally. However, you can also do this with a 2-dimensional one, right? You can also do the same things here. You have the 2-dimensional, you have just reduced vector space here because it's a 2-dimensional, not a 3-dimensional. And then you can do also the diagonalization here. You can get also then the eigenvalues and the eigenvectors. And you can build up out of them, let me say, the parameter space that is the same as here. So just in terms of mathematical, the same, it is only reduced in terms of parameter space. And which means then also that the interpretation for sure is not completely the same, right? Because you have a reduced information space. However, still, what you can do, you have still kind of randomness here. So you can still interpret entropy normally is interpreted as how many scattering mechanisms do I have in my resolution cell, right? You can think about this, how many do I have? So if I have strong entropy, it means I have a lot of scattering mechanism. If I have low entropy, it means I have only one dominant scattering. And here for alpha angle, we know we can identify the type of scattering mechanism, that which type of scattering mechanism do I have. If it's low alpha angle, I know I have surface scattering increasing it, going to volume scattering, and then to dihedral scattering. So that's in principle our scattering mechanism, which can be also done not as good probably as with a full pole, but still it's valuable and can be used. And I'd like to show you how this does look like. Again, a scene here now. This is a scene taken from an aircraft, from a Japanese aircraft over a Japanese city, which is Gifu. And you see we have here urban areas and some kind of hilly areas here, more smoothly. Also agricultural fields here and a greenhouse, this one. And if I look now the entropy, so the entropy and alpha plots that you have seen already many times, you see you have a kind of big space, parameter space here inside of all the pixels that are here, right? And you see you have the majority is here on high entropy and kind of medium, let me say alpha angle, or even going to higher ones, which means I have a strong contribution from the city, but also here from the greenish part. However, if I have now a reduced parameter space where I have, as we said before, only the HH transmission, so I have a HH and a cross pole, then, and I derive with the same thing that I've shown before, the two-dimensional diagonalization and derive the entropy and alpha parameters, then you see you have a reduced parameter space that you get, right? It's just like lying here somehow in this case. If you transmit V, so you would have VV and VH, so co-cross. Again, you have a kind of reduced parameter space. And if you go now to this copol, HH and VV, you see you get a little bit more information space. It's not the same as here, right? It looks a little bit differently. But still, you see that the parameter space is a little bit opening up. So you have a wider range of information that you potentially can use if you like to do, for example, classification or any kind of other information retrieval from it. Okay, I've just done this also as an example then with the HH and VV part for different surfaces. That's again a smaller part of this Gifu area, therefore this looks differently, but this is the HHVV part. You see this is a glacier here over Svalbard, which is very dominant, so it has a very particular signature. This is also a mountainous area in France, the glacier Argentière, where you see you have a different feature again, and that's a normal rural area where you have agricultural fields, and you see again, this is a little bit the shapes of these and the information content is different, which is interesting, right? Because you can use still this information, even though you have only two polarizations to do some differences, or in principle, it provides you information of what is on the ground using, in principle, this two-dimensional polarimetry. Okay, that's was a little bit of excursion to tell you, okay, you can also use dual pol, which is important, and can be still used even though you don't have the cross-polarized term. However, it's clear having full pole data is always better, it's for sure. But if you use copols as such, just it is also very interesting and useful to be used. Okay, I'm just switching now to, in principle, the Great Aletsch Glacier, which we started with, and this is also the glacier which I'm using in order to later on also to do the exercises with you. So the Great Aletsch, so the shape that you see, this is again the shape of the glacier that we've seen before, and this is it's called the Great Aletsch Glacier. It's located in Switzerland and is still one of the, let me say, longest and more massive ones in the Alps that you have, with a length of 23 kilometers. Quite big surface, as you can see, and it's in terms of elevation, it's ranging between 1,800 to 3,500, which means already you're quite high, and in these very high locations, you could also have a lot of really dry snow, which is important because what we like to do now is to estimate snow height. And for this, we would also need dry snow because for wet snow, and this is what we will see later on, we have some difficulties. Okay, what is also important to notice, even though it's high located since 1881, we have a dramatic decrease of the glacier itself, or just from the mass. I mean, that's quite clear, where we see we have up to 4 meters per year, where the front of these here the glacier tongue is retreating more and more. So that's quite strong. And the equilibrium line, which was here stated, it is on 3000. We'll explain what the equilibrium line is in principle already shifted. So that's a result from 2018. So you can imagine in the last summers, it was very hot. So this equilibrium line is shifted more and more up nowadays. However, we are using tandem X. We will use tandem X data, as you see it here. So these are the data as I explained before, and these are the dates here for what we're interested in to see the winter season mainly over this area. And we started to acquire data from 2011, and you see then to 12 to 13, 13, 15, and so on. So the most, let me say, with a lot of acquisitions, really between 11 and 12 to 13, I would say. So this kind of winter season. And in the exercises that you will see later on, these are the data set here, which are these one, the bluish one from 15 to 16, because we have quite a lot of different acquisitions that you will use and you can analyze them. Okay, this is the Concordia place that I was mentioning before. This is the place where the different glacier masses are coming together. And do you remember this part here? These were the crevasses. Somebody was identifying this very well. This is an optical image just taken there, where you see here strong crevasses, and otherwise it looks quite smoothly. You have also some rocks in between. So this is how a nature looks like, or how the Aletsch Glacier looks like in this region. Sorry. Okay, so what you see here now, this is the evolution of the sigma zero, so the radar backscattering intensity of the Aletsch Glacier. For this is the same as you have seen before. So this is in principle the Aletsch Glacier. You have different colors on the glacier, and this is starting from November 2011, going to let me say December, January, February, March, April until May. And in May, June, normally we expect that we have strong melting. So normally the first snow is coming in November. This is the typical situation that we have in over these alpine areas. So in November, snow starts, which means then also that the glacier, you see it here in the radar backscattering intensity, the glacier looks quite bright. And it's getting brighter, so it's not changing so much. Some parts probably change. This is getting darker. This is again brighter here, the tongue a little bit and going. And then you see it's getting dark again. You have a darkish area from April, where we expect also to have higher temperature already ongoing. And here until May, you have it's really dark and getting darker. And even these parts is still bright. That's a higher location of a glacier tongue, and this one is getting now, you see from May to June is also dark and everything. Even the upper part, which is around 3,500, the really flat upper part here is getting very, very dark. So which means we have a lot of, so the darkness means I have a change of the property of the glacier, so from bright to dark. And I will just explain now why this is happening actually. So we have seen in the winter months, we have bright colors over the image of the Aletsch Glacier, as you see it here. So that's quite bright. And even this one is even brighter because it's higher located. So they're very bright. And if you go now, that's just a sigma zero. If you go now to a summer image here in May, for example, it looks very, very dark, right? And the question is, what is the difference? That was a good question before. So why is one dark and why is one bright? And this has something to do with the scattering and the temperature of the temperature of, let me say, of the atmosphere, which is influencing the property of the snow. So what is happening with the snow, and then also how strongly the wave can propagate or can penetrate into the snow volume. So on the one side, you see if it's very dry snow here, what is happening, I can penetrate with my wavelengths, in this case it's the X band, and I can get scattering within my snow layer. So I have multiple scattering contribution, which are all then transformed or transmitted back to the sensor. So therefore, here everything is very bright. So I have strong energy coming back to the sensor. What is happening in summer is because the surface is melting, right? You have a melt region that you're not penetrating because it's a kind of water, small water area on top. And if you have this water area on top, you are not able to penetrate, probably only a little bit, depending how much, but normally it's kind of water surface here. And then the whole energy is going away from the sensor. So the darkness means always I have high temperature probably, and my surface here is wet. So therefore I cannot penetrate. So the dark and bright things, just if you use these intensity images, you can already distinguish between winter and summer scenes, or about the temperature. You can already say, okay, it must be now wet, right? Because it's a temperature difference between those. So that's very interesting. What you see here is the digital elevation model. And you see here now already that these parts are higher located. If you go back, you see also that this part is always the latest one, which is getting really wet, right? Because it's higher located and keeps still the brightness. So it's still bright until here, until May even, whereas the rest is already dark, which means it's already water on the glacier. And here now slowly it's getting also dark. This means also the higher areas are getting melted in terms of, or getting wet snow. So therefore you have this difference. Okay. And here, what you see now here, that's the entropy in the alpha images. So this is taken with a two-dimensional, right? This is not fully chromatic, what you see here, but it's really two-dimensional. So the two-dimensional scene of entropy and alpha, because we have only HH and VV, so you can also do this. And what is interesting for the entropy, you see you have higher entropy over areas where we know we have strong crevasses, right? Which seems reasonably to be like these, so strong crevasses here, so therefore high entropy, more scattering ongoing, and this here on the more flattish area you have a lower entropy. And what is interesting for volume, it's still higher in total from the scene for volume scattering as if you would have surface scattering, because it's clear in winter you have a change in terms of the scattering mechanisms, because you cannot penetrate so strongly, and therefore you get here low entropy over certain areas, as you see, or lower entropies in general over this area, as for example in winter. Also these, therefore it's very interesting to have also entropy and alpha, because you can also distinguish the scattering mechanisms that are ongoing. And for alpha, again, we see we have a higher alpha in summer because we have more volume scattering, which is clear, and a lower alpha in winter because we have only surface scattering. We see it also here. It's very strong surface. Okay, scattering mechanism vary with snow and ice condition. That's clear, and also within a single scene, right? You saw it also already that within the single scene you have the differences. What you also see here now is again the same time evolution for entropy. Again, we can start here in August, where we have, let me say, we assume to have wet surfaces, so therefore low penetration, low entropy, and then the entropy is increasing with the volume and with the dryness and the accumulation. Probably you have also some snowfall in winter. So that's increasing, and you see really how strong some parts are stronger increasing than other parts, right? So that's quite interesting. And then again, it's going low and low because slowly we're getting more and more wet surfaces, and therefore we cannot penetrate and get, in principle, the surface scattering in low entropy. The same is actually for alpha. You've seen it already before, only for one scene. Now you see it here for the whole series, again, starting with August. So wet surfaces, we see here very, very low alpha, and then increasing when we have the first snowfall and the penetration then into the snow, the dry snow. And you see also here some regions are particularly stronger than other regions, for example, right? That's also very interesting. So it's changing also spatially within within the different parts of the Great Arledge Glacier. And then again, when it's starting warming, you see already it's decreasing very, very strongly because you have then only surface scattering ongoing. And this is interpretation again of the two-dimensional entropy alpha, which is interesting, right? Also can be used very well. Okay, I was before talking about equilibrium line and the glacier itself, how the glacier look like. And we have in principle, we can distinguish two big parts on the glacier. The one part, which is the lower part, is actually the ablation zone. This is a zone where we still have snow cover ongoing, right? But where we have in principle then pure ice. Whereas in the accumulation zone, what is happening here, we have also snow cover, and the snow cover is going into firn, which means is a mix, let me say, and then really below to real ice. And in this kind of firn area, we have a lot of different heterogeneous structure. For example, here we have ice layers within the structure, within the firn, or we have ice lenses, for example, or pipes, we call this sometimes, so it's depending a little bit. So, but very, very compacted, let me say, snow cover here before it starts really to be ice, which is below even then. And I said before, the equilibrium line is in principle the line between the ablation, so more is melted than accumulated. So accumulation means I'm getting snow on top, but in the here also an ablation zone, but in ablation zone it means it's more melted than I can get snow on top to increase snow or increase in principle the glacier mass. So therefore the equilibrium line is between them, and this one now with climate change is shifting more and more up in principle, which means we have always more and more snow melt and more glacier melt, and we cannot retrieve it anymore. So that's a little bit the point. And we have this situation we have also on the Great Arledge Glacier, where we have in principle this part, at least in 2018, still is a part which is in principle the accumulation zone, and this lower part here, therefore it's separated, is a part which is the ablation zone. So we have these two parts, and what you see here now is nothing else as just this time series of the sigma 0, which is the radar backscattering intensity, which you see here very well. So for the ablation zone, which is the lower part again, we have lower values, right? Because this is what we saw already before. In general, they are lower also over the time, even in winter sometimes, right? And then we see here in the bluish one is the accumulation zone, where we have snowfall and accumulating more and more snow. So that's the colder region, the colder part, which is always in terms of sigma 0 always higher. The other lines that you see here, which are these dotted lines, are in principle the standard deviation between of these ablation zone and the accumulation zone. If you look now again for entropy and alpha, we saw it already before, so it was already visible. Here's only just that you see it also in terms of values. How strong does it vary? If I take now a mean of the ablation zone or accumulation zone, and again also here, if it is only a mean, right? Therefore, you don't. There's a lot of structure also ongoing, so you don't really see them very well here. But that's again also the accumulation zone is higher in entropy than the ablation zone, and the same is actually also for the alpha angle visible here. Okay, yeah, I think that's what is just interesting, is to see that you have also interannual dynamics. That's now done over several years that you can see here. So starting from 11, 12, 13, 14, 15, and until 17. So these are the different years. And within these years, you see also that you have in principle this variation. That's a sigma 0. So you have a variation from low radar backscattering intensities going up during the time where we have strong snow cover and snowfall, and then going down again when we have melting ongoing. And this in principle, you see it very well also with a variation here. So that's perfect. The same is for entropy alpha. Oh, sorry. The same is also for entropy, and the other one is then, I don't know, the other one is then also for alpha. So you have these variation that we have seen before, just that you see it's also happening sometimes stronger, sometimes less, a little bit depending on the season, how much how warm it was also in winter, right? That's very important. And how much snowfall I had. So how much precipitation I had. Okay. This is now the parametric phase difference. This is a parameter that we can estimate directly using HH and VV phase. So it's quite simple. And here you see these are the main things that we have seen already in entropy and alpha. We have seen that the coherence, so the phase, no, not the coherence itself, sorry, but the phase here, the phase difference between VV and HH is varying. So everything that, let me say, is around greenish, it's around 0 probably, right? It's a little bit stretched here. So because the phase can vary, because it's a phase parameter can vary between minus 100 degree to 180 degree, right? This is a phase estimate. And if you go now again from August, from summer to December, you see already that you have a phase shift here towards the positive values. If you have positive values, it means that you, and you see it here already, that you have accumulation, which means you have snowfall, which is in principle adding to this information. So fresh snowfall produces your positive kind of value. So therefore, if you go here in this direction, you get more and more positive. You have also a wrap. You see it here where you have reddish parts. So it's wrapping once around. So this can happen sometimes if you have very strong fall, right? So then the scale here doesn't work anymore so well. And then if you go back to, let me say, when the snow is again settled down a little bit, even though if you have no snowfall anymore, it's settled down, what is happening with the phase here, it's also changing the signature and is becoming again more to a greenish 0 and is going a little bit actually also to the negative part. So therefore you see this getting greenish or greenish, and if it's very, very green, it means already you're here in the negative part. So this is already the either it means you have warming ongoing, so it's temperature there, or it means you have the change of the because of the temperature, you have and you can still penetrate into it, right? You have a change of the snowpack in terms of recrystallization of the crystals itself. Okay, and why is in principle VV and HH, the copol phase, so interesting for snow height estimation? Or why is the snow depth proportional to it, right? Because what we saw, this could be an indicator on how strong or what is a snow height estimation. So there have been a lot of different studies which were showing this, and there's in principle 3 points which is important to remember. So the first one, the fresh snow causes the highest phase difference. So this is what we saw also in our images already without knowing it. So we have a phase shift, and we have a strongest phase difference that we can see also in X-band. This has been observed even in higher frequency, as you can see here, 95 gigahertz from Chang. The second thing is what is important, that what causes a difference in HH and VV in the snowpack, what is the difference, what it really causes to be different is in principle the orientation of the particles within the snowpack. So this is something, and they are polarization dependent, right? So therefore you have also, you have a different propagation of HH into the snow than from VV, right? So this is why you have different propagation lengths in the snow and scattering. So first propagation length, so that's the first part, because the particles in the snow are oriented. And then the other thing, the third part, which is important, why it is, why there is this relation is in principle the recrystallization of snow changes, the shape and the orientation of ice grains, which means if I have no snowfall ongoing, but still dry snow, I can still penetrate. But what happens in principle if I have no snowfall is I have a change in my in my volume actually. Okay, perfect. Good to know. Thanks. So these are the 3 points. And why is this important? I show this here. So what you see here, this is a computer tomogram of snow. This is a snowpack that you see here, and you see probably it's a little bit difficult to see it. I needed also a long time to look at it, but if you look very fresh snow, so week 0, this is a fresh snow of around 10 millimeter, And when snow is falling, you see it's falling down to the ground, and it's a little bit getting a little bit, you know, you have big crystal normally, but it's a little bit flattening. So this is very fresh snow. Then what is happening after week 4, when the snow is in principle stable, it's not falling anymore, but it's stable, it's just compacting, right? It's settling down. And what you get is kind of these shapes of particles. So it's a little bit elongated shapes that you see here. So there's elongated shapes, and therefore what is happening actually, and then in the week 12 already here, we see it even stronger. You have very strong shapes like these, like needle shapes, and these are oriented somehow. So what you have with time, if you look now to real snow properties here, you have a change from horizontally, let me say, more expected snow crystals to trying to get into the vertical extended. So what is happening really in snow is you're getting from more random shape or horizontal shaped into the vertical extent. And therefore you see also the differences. So if you penetrate into dry snow, you see first a difference here, because you have an orientation effect already in the snowpack. And then you see in the metamorphism of the snow, even then you will get differences just because of the difference of the snow itself. Oh, sorry. Yeah, I just go a little bit further now, probably a little bit faster, because what you see here is now a theoretical plot where you have HH and VV phase, right? This is a phase. And this is a little bit what we saw in principle, how the grain size looks like, prolate and oblate. So these are more the prolates and these are more the oblates. Oh, sorry. No, it's not true. That's a horizontal and the vertical. So prolate, oblate, it means they are horizontal or vertical oriented also. However, what you have, if you don't have snowfall, then you have a negative value of HHVV. And if you have fresh snow, as you see it here, you have positive values. This is just the different lines. It's just for different incidence angle that you can see here. And this is just also for different densities, because density of the snow is also important to be considered if I look now for fresh and dry. So, and if you have this sketch already, then you can really invert in principle from this HHVV into this axial ratio of grain size. So you have an interpretation of these two boxes here into your image. So because you know around what happens if I have positive degrees and what happens if I have negative degrees. And out of these, a model has been developed, which is actually really considering these different structures within the snow. As said, this is considering in principle 2 parts, so in principle the structure of the grains that you see here. And this is done by the degree of anisotropy, where you have this axis AZ to AX, or epsilon here to AX, which is in principle the axis of these part so first the axis of the shapes, and then also the lengths of these parts, which are all related in principle first to the degree of anisotropy, so how the shape is. Then the second is the permittivity importance, so how wet is my particle, and at the end is in principle the refractive index, inside the snow. If you have built up a volume with these particles, then you need also to consider what is the penetration into it. And this you see here. So that's in principle my snow here. I have different refraction indices here for different polarization component. And my volume is considered in principle to have maybe 4 components, which are important, which is seen here. So you have the HHVV, and this one is modeled in terms of the thickness of the snow and the wavelengths that we have here. And then these whole part here is actually a function of the degree of anisotropy, the density, the incidence angle or refractive index here. So this is in principle the main parameters which are important in order to model the HH and VV. And if you invert this, because you know you have the height here, you can do the inversion out of the height, then you can also get the height estimates. What you see here now are sensitivities of the model to the snow. The one is saying that I have an increase of the sensitivity with wavelengths. So that's one part. Then the other one says I have more sensitivity for higher anisotropies, so degree of anisotropy. Here, this is more a complex situation because it's going to the density of the snow. You see we have a kind of ambiguity, so it's increasing until a certain part, but then it's again decreasing here for higher densities. So that's for medium dense, it's possible to do it, but not for very, very high dense media, depending again on the wavelengths. And then the other thing is then we have a linear relation to thickness. And this is something that we like to have because this is something that we like to estimate then from HH and VV polarization. Okay, I have just a short view on that you can also do it in very high frequency using a spectrometer that is in principle here is called SnowScat. It's a sensor which is illuminating different sectors. So that's a SnowScat instrument illuminating the sector 1 and sector 2 in 4 different incidence angles, as you can see here. And we have, in addition, also radar target calibrator that we can use. We have a ground station for kind of snow water equivalent estimation, and also kind of snow pit densities. And there's also an automatic weather station. So this part has been analyzed, mainly this sector here, in order to see if we can do really snow height estimation, and if you would have a very strong relation to HH and VV. The acquisition you see, it's really perfect because it's every 4 hours, which is very good in order to see if I can detect fresh snow. What you see here now is using actually the SnowScat, but also at the same time we had also TerraStar X data. So in time, the data, which is only, do you remember, we don't use interferometry, only one single slot, and then we compare the different HH copol estimation to each other. And if you now plot just the HH-VV against snow height, you see you have a quite strong relation, even though you have strong variation too within these strong relations. If you look now for the change, so what if I do a change between one single point to the other one, so that's a change of the CPD, then you see it's even stronger related here along the line for different regions here, the bauxite and the main area and the mean value out of these two. And then what you see here is just a SnowScat for this 4-hour difference. This TerraStar X normally is 11-day difference, and this is 4-hour difference within this 13 days. And here also here you see you have quite a lot of strong correlation between the HH, VV and the snow height, because that's what we like to estimate, to see is there a relation. You can also then compare this with the snow depth, so that is measured on ground. This is the accumulated snow depth that you see here, and the temperature. And if you now look to the HH-VV phase that you see here for snow, for TerraStar X, but also for the SnowScat, then you see there's quite a strong relation between them on areas where you see that I have a little bit warmer regions, so they're still below 0. Here, these are below 0, right? But it's close to 0. These are the hottest areas. And then you see the coldest areas, which are in green. So in the cold area here, there's below 0 quite strongly. You see here also a decrease, a settling down actually of the, in principle of the signals that you see. And the same observation is done between satellites, but also the kind of ground measured station. Okay, I'd just like to go now further on to the available ground measurements. Now back to the Arlich Glacier. This has been an area in Sudankali in northern Finland. And if you look now to the estimates in over the Arlich Glacier, then what we have available there are fresh snow heights from 16 and 17 for a certain density and a degree of anisotropy, so the inverted one and the measured one. And then we have also the total accumulation of the snow, of the different snow events. So you see there's some snow events here. And if you accumulate them, you will have these kind of peaks where you have strongest, let me say, snow height accumulated over this time. Okay, if you look now to the copol phase, again here, that's a copol phase, 16 and 17. what you get is a coupole phase which is varying between December and May. And we know already that for fresh snow, we have an increase, let me say, of the height. And when snow ages, then in principle, the height or the phase is in principle staying the same. And this is as seen also here. So we have here again the measured one. So now inverted, the coupole phase inverted into height using the model. And this is now, let me say, the accumulated height that you see here. So the measured one with the with tandem X. And here, these one are for different densities. So that's a model, the degree of polarization for different models, just to see which of these models fits best, let me say, to these kind of measurements that we have here. And you see it's a little bit depending, right? Not all of them are right. It's probably very variable, depending also if what was the temperature on the time when the snow was falling. Therefore, also the density is different, right? So therefore, probably not one is fitting best, but you need to have a variation of density that is fitting really to the data that you have. Okay, and below you see again the temperature and also the air temperature, which is mostly below 0, but sometimes also quite high. Just going back, sorry, I'm too fast. Okay, so I should stop slowly. I see it. Okay, so I'm just, I think I can stop here anyway, because what you see here is in principle the April. So these are the times where we have areas of, is it right? Of more colder or more warmer areas. You see it here. So it's going to 0 degrees in this case here. This is lower, which is colder regions, and this is higher. So therefore we have also here a decrease. You see it a decrease because it's warmer temperature, and you have a decrease of the height, which means also a decrease here in the HHVV polarization, right? So the phase variation. Whereas all the rest is increasing, which means we have an increase of the values here with this peak, and this peak. So these are the 3 peaks which are increasing. So we have a very good correlation between the height and the coupole phase and the temperature. Okay, that's just to see that we have the same also in 2011 and 2012. I think it's the same part that we can see, because it's just a different season. I mean, it's the same season, but different year. We have different things ongoing, right? So you have already strong melting from May here ongoing. Therefore, this is kind of line. And we are already having also some compaction ongoing in this area. And you see already, depending from season to season, you would have a different kind of behavior of the snow and also the estimation of the snow height. Okay, just saying the limitations, it's clear that everything that is higher than 0 degrees, this would not work, this method, right? Because you cannot penetrate. It's only possible when you penetrate and you see the volume, right? So that's one thing. And the second thing is during the time of compaction. So when you have the metamorphosis ongoing of the snow itself, where you have the crystals are changing, right, within the orientation within the snowpack, then also here there could be a problem. Okay, it's clear why this snow height is important for different kind of applications also. This is just again said here. So one important parameter is also snow water equivalent. But yes, the other parameters are very important in terms of for hydrology, but also for climate change estimation, also for the water availability for vegetation, any kind of risk management, very important nowadays because we have a lot of avalanches ongoing in the Alps and a lot of dangerous events there, even floodings, and also important for weather forecast and so on. Yeah, so that's in principle concluding a little bit my part, and I would like to stop here. I have still some slides which I can provide to you, but I would just not go now through it. I think this makes a good end. And I just have a last, what I like just to mention, I'm not sure if this has been already mentioned, that I'm just doing it here, is this one. So if you like to know more about different kind of applications, there's a an open access book available, so you can download it. What is important or what is interesting here, you have also the basic principle of polarimetry there, and you have different application areas. So it's not only snow, what I was showing today or yesterday, forest, but you have also other kind of urban areas. I think urban areas is not covered here, and ocean. So you can also have a look there. And what's also important is not only the theory there, but there's also code behind. So there's code provided, which you can also then have a look, and you can redo in principle the computations. That's just my last word to you. My word to you. Yes, right. Okay, good. Thanks a lot. Do you have a fast question? Otherwise, we can also do it in a break or later on in the exercise. Yes.
This glacier, the red snow is there or ice?
Is both. Here is both. So you have an ice which is below. But it's only on the upper part. It's really ice, strong ice. It's also in the lower part. You have a lot of ice, right? It's both. You have ice everywhere, but then on top, in the lower part, you have only snow which is coming there. But this snow is melting, and so therefore also the ice is melting. So therefore everything is retreating in the lower part. In the upper part, you have more and more snow coming, then it can melt. So therefore the ice is still fresh there. So the ice is still there and can stay there. So therefore the upper part is always brighter because you have more scattering ongoing in let me say, or because it's higher, you have lower temperature, right? You can penetrate. And for the lower part is faster melting because it's getting much faster warmer. So therefore you have the specular reflection much stronger. But you have it already, you saw it already in summer, you have over the whole glacier. So the whole glacier is affected by melting, even in 3,500. And I would assume also in India, in Himalaya, you have a very, very strong impact already on warming up also in higher regions. And therefore you get it also darker there. But however, normally you have always dark ice. So you have no dark, so you have ice below. Then you have a fern zone where you have the mix between fresh snow and ice. So it's a kind of mix. And then on the top, you have fresh snow always. So these are the three categories that you have. But that's only for these temperate glaciers, right? It looks again differently if you go to Greenland or if you go to Antarctica. The construction is different a little bit, and also the structure inside is different. That's only just for the glaciers which are completely also having the temperature, so completely melting actually. Very strong temperature gradient in winter and summer. Okay. Some questions? Otherwise, okay, now then we just do it in the break, and I just give it then over. I'm not sure if it's a fast change. It's not so much, sorry, Armando, I was taking your time already, the 15 minutes, but if you like, or if you do, I'm not sure if we can do already now a break. That would be a nice thing too. No. Okay, we have check if it's already, because it's good to have a small break, I think. Oh, perfect. Just fresh a little bit. And oh, let open the door. It's so, I think, sticky here inside, right? It's getting warm again. Okay, see you then later. So then we would have now half an hour break, I would say. So you're coming back, yeah, on 10:40, I would say, right? No, sorry. How much? Okay, so then we do. let us do 10:30. Okay, 10:30 is a compromise. 10:30 is good. Perfect. So take fresh air. Thank you.
Thank you, everybody. Need to try to find the right distance. I think it's a bit too loud, isn't it? So, anyway, I hope it's not too loud. Otherwise, if it's starting to be too loud. So, welcome everybody to this. Is there a way to measure the? Is there a way to reduce a little bit the volume? It's okay? Okay, very good. So welcome everybody to this part of the course today. I have to say, for me, really, it's a pleasure and an honor to be here. I remember I was in your seat 15 years ago, coming to an ESA course, and that really blew my mind, really. I changed the way that I was looking at my problems. I came home with more questions that I came back home with more questions that I had at the start, which I think is a good thing. So this is what I wish for you, that you come, you see these things, and you will have more questions than then you started. And then you can start tackle those questions. So a first introduction about myself. How do you change the slide? Is that normal? Yeah, try again. Okay, I think that is okay. These things will disappear automatically, right? No. So it will be there. Will accompany us. It's a very good place as well, because you cannot read the title.
Okay, let's try this again.
Okay, it's working. A quick introduction about myself. So Armando Marino, I'm an associate professor at the University of Stirling. Stirling, for the one that don't know, is in Scotland. It's not far from Edinburgh. And it was a capital of Scotland at that point, but then it stopped growing when Edinburgh grew. So that's why it's a small place now. But it's a lovely historical place. If you are around in Scotland, please come visiting us. We are not very far from Edinburgh or Glasgow. So anyway, let's start with what I would like to talk today. So we'll start with a quick recap. Then we talk about some maritime application, which I believe you have not heard so far. And then something related to change detection, can be related to agriculture, urban, or hydrology, like floods. Also, I believe we are finishing at 12, right? When it's time, please let me know, Magda or somebody, because I can continue for very long otherwise. So naming convention and say warming up. So you have listened to different people here. Everybody of us has their pet words to use. We may have slightly different language to refer to things. So I would like to start with this thing here. So we are on the same road. When I say a word, you know what I mean. So you have seen that the biggest separation so far that we have for target in polarimetric scenes is single and partial targets. Single targets can be characterized by a single scattering matrix, which is this one, also called Sinclair matrix by somebody, that you can vectorize and make it into a vector. And if you have symmetry and reciprocal medium, this thing is three-dimensional. So you have this three-dimensional vector to work with. And if you normalize this vector, you get a normalized vector. This thing is called by many a scattering mechanism. What I like to use often is this word projection vector. Because if you use these things inside an operation, which is not really referred to something that is there on the scene, that is not really a scattering mechanism as such. It's a potential scattering mechanism. So that's why I use a different word. While when I refer to something that has been extracted by the algorithm, I call it scattering mechanism. So for me, you can interchange these two things. It's okay. In my head, these are separated. But this is what I mean. I mean the normalized scattering vector. Then you've seen these are tricky. It's tricky to work with coherent targets because there is speckle inside images. we have seen the wonderful things the speckle brings. So what we need to do, we need to deal with it, and we do it by using second order statistics. So doing the outer product of this scattering vector and averaging that. The averaging is the most important thing. It's very important also this bit, but averaging is very important. If you get a covariance matrix, but you do not average, it's like you're not doing it. You're not getting the second order statistics. Average is important. And you do the average by each component, blah, blah, blah. So what you get is intensity on the diagonal, cross correlation on the diagonal. Covariance matrix, I refer to this one. Using Polybase, I call it coherency matrix. I think you have already seen all these things. The thing that you may be helpful for this part of the practical is this fancy things here, which is a quadratic form. So what you do, you take your covariance matrix and you multiply right and left for your projection vector. These things, these magical things, gives you the intensity of that scattering mechanisms identified by the projection vector. So you have the polarimetric space, you know, this three-dimensional complex space, and there are so many things going on there. There are different vectors going in different directions, and I'll show you more of that later. But if you want to know a specific scattering mechanism, say the double bounce, then you can extract it by using the projection vector for the double bounce, put it inside this equation, off you go. You know the intensity of that type of scattering mechanisms. So this is very powerful mathematically, and you'll see we will use this many, many times in these slides. If you're curious, you want to know why these things is the power of a scattering mechanisms, have a look at this demonstration here. I leave this to you because I don't want you bored to death. So now what I would like to do here is also to be a little bit more interactive. So I scattered my presentation with questions for you to answer. This is called Poll Everywhere. It's a freely available website. So if you scan this QR code, you will be seeing a question there that I just activated. You answer your question, and then I'll show you the results here. And hopefully this works. So the question you have to answer is, what shape do covariance matrices have in the intensity space? And then, are they cubes? Are they ellipsoids? Are they donuts? So there is this space full of vectors. Laurent is here. If you can throw the pen, I can try to draw it there. No, it's not here. Anyway, I suppose nobody has a whiteboard pen. So, but anyway, imagine that there is this three-dimensional space with vector going everywhere. When you start averaging these things together, they will form a shape there. Which shape is that? And I think nobody knows, but just for fun, I would like to see what you think the shape is, and then we talk about it. Okay, ellipsoids, you know, very good. Very good. I should not have said that you don't know it. That's right, they are ellipsoids. Very good. Donuts, we are hungry, but unfortunately they're not donuts. It will be fun. So now, I need to go here, right? Very good. So, the shape that this quadratic form create, if you sweep all the omega, all the projection vector, the shape that they create is this ellipsoid. So there's three axes, major, middle, and minor axis. It is very hard to see from here. But anyway, this is an ellipsoid. And I plotted this on a fake base. So this is a three-dimensional real base of axis. In reality, it's not like that. In reality, each one of these is a complex number, so it's two. There is no one line. there is 2, so it's 6-dimensional. But if I try to plot this here, I will make ridiculous of myself and you won't understand anything. So I keep it simple by being real. But keep in mind that this is just for you to understand what is going on, but it's not the reality. The reality is more complex than that. There is more dimensions there. But anyway, there is this shape which is an ellipsoid there. So you change your omega and you get this vector. Then you change, you get this vector. You change, you get this vector. This vector, this vector, this vector. When you put all together, you create this ellipsoid. This is the best picture I could find of ellipsoid on internet with these 3 axes. This looks like, say, what is going on here? Why you are telling us this? But it will be useful later. You will see. So also I like to make it, give you some hints that help you remember things in the future. And so I put funny things sometimes. So for me, this looks like a spaceship. So if you maybe, with this hint, it will be easier for you to remember in the future. And when you come out and somebody asks you, what is the shape of the covariance matrix? You may think about the alien and come back. So if you come back out of this lecture, you remember this thing, I will have succeeded. So anyway, I think this is a spaceship. Sorry. So first application, maritime, first part of the presentation, maritime applications. And so here I would like to tell you about some algorithm that we use for detecting objects in the maritime domain. And if I ask you which kind of objects we normally want to detect in the maritime domain, what will you say? Ships, isn't it? You saw the slide. So ships, indeed. I think the 99% of activity is about detecting ships. So it's so common that I don't want to talk about it here. I want to talk about something a little bit more niche. But indeed, ships is the most important thing to do. And one of the important part is to detect illegal fishing vessels. So there are restrictions in areas and some vessels still go there. You want to be able to detect it. But also there's many other applications related to ship and vessels. But to make it a little bit more fun and more environmental, say, I will have a bit more different type of targets. The first one is icebergs. So what I did here, I put some information about this type of applications. I don't have time to go through this right now, but the slides are there, you can have a look, because I think it's important also that you don't just see the methodology, the maths, the physics, and all these kind of things, but also to understand why we do it. So why icebergs, who cares? So there is some information there that you can read, but there is not much time for me to go through at the moment. So one the good things of polarimetry, I hope you appreciate at this point, is that we can separate different targets. Different targets behave in different ways. So what we want to do here is first of all to understand if you expect icebergs to behave differently than sea ice or the ocean surface. Now, icebergs are made of freshwater ice. You have seen half an hour ago that there is some penetration inside this freshwater ice and there is some volume scattering. And also if the ice is wet, there will be things bouncing off the walls crazily. So while on a surface like the ocean water, the penetration is very small. So the electric constant of water, of salty water, is very high. So this means very small penetration inside, and a lot of it goes off specular or just stay on the surface. So it calls for surface scattering. If you have sea ice, things don't change much. Sea ice is also full of salt. So it's still there very little penetration, unless it's some very old multi-layer ice that is as dangerous as icebergs, maybe. So this couple of meters, see very old multi-layer ice. But in that case, you want to detect it. So surface scattering for what is called the clutter, the background, volume of multiple orientation for the icebergs, bingo. Maybe pulsar can help. And Another thing that is quite cool, and I think there will be more and more in the future, is about related to aquaculture. So we know aquaculture can provide food for the future, can feed the planet, good amount of proteins. Unless you are vegan, that you think eating fish is a good thing for the future. So there will be more and more, whatever your views are about that, there will be more and more in the future of aquaculture. And there is the risk that some of this may be illegally placed in places that they shouldn't be there, or the water is polluted, and all these kind of things. So you may want to think about monitoring these aquaculture cages. This is an example on the Vigo in Spain, Galicia, and not because they're illegal, but just because there are so many. So it was easy for us to we collaborate with some people there. So it was easy for us to work with those aquaculture. That's mussels there mostly. So again, go to the scattering that you expect. The scattering mechanisms is a little bit like the icebergs. I just copied and pasted a different picture on the back. You see it's the same stuff. So we can still do it. We can still have some separation inside the polarimetric space where C will be in one direction. The rest will be in the other direction. By looking at the polarimetric space, we can say this is C, this is the rest. So this is our target. So now, question for you. This is R-ship single or partial target. You have seen what are single target, what are partial target. Now, let's talk about ships or even icebergs. Are they single or are they partial? And then I have to go instruction. This one, activate the second one. So now you should be able to vote on the second one. And also take this opportunity while you vote to think about it. So the purpose of the exercise is not just to entertain you, but also to get you to think about it and come with questions. If you say, well, what is going on here? That is your point to, and come with the question. To give you the little. So 15 people, 16, come on. Single, partial, or it depends. And also give me a chance for a drink. Okay, let's see what people think. It depends. Very good. I think that is the right question. And normally that is the right question. Whatever is the answer, whatever is the question. It's always it depends. So let me set to the next one so that then you, oh no, ask me later. Okay, so let's go back to the slide. So why it depends? So now, you know, a vessel is, if it's very small and the resolution is very big, so the vessel is inside a single pixel, you get one single pixel for the polarimetric acquisition. So you get 3 measurements, HH, HV, VV. So in that case, the things is as well as a coherent target. You cannot really discriminate. You have one single, anything with one single pixel appears as coherent, just because you cannot see the speckle if you have one. So one vessel is very small, you can as well think is single, it's okay. You cannot do anything better. Of course, if you change the orientation, you change the incidence angle, you change the frequency, it will look different, but it in itself is a single target. However, if your things is big, and again, it would be nice to have something to draw it, but let's imagine that. Imagine that your things is that this big here, you have many pixels, you have 1, 2, 3, 4, 5, 6, 7 pixels of the ship. So this is the what you call the back of the ship, the bow, and this is helping to the British people. How you call the back of the ship? The stern and the bow, I think. Okay, so anyway, the back of the ship will look something, look like maybe there's a crane there, and there's a certain figure. The middle, maybe it's double bounce. It will have a different polarimetric behavior. The front, you see the rail, is a different polarimetric behavior. Each single pixel of the ship is different. It's not a single target anymore, isn't it? The whole thing is not single anymore. But it's also not a partial target because that is not speckle. What you see there is not the different realization due to the interference of the scattering inside the scene. They're all the same stack, all the pixel of a crop field, but each one is a bit different because of speckle. This no, you see the crane, you see the freeboard, you please help us outcome these things. How do we deal with this kind of targets? They're not single, they're not partial. The speckle is not fully developed. How do we deal with it? So this is a challenge for you to bring home. So anyway, it depends what you are really, how big is the ship and how you look at it. So let's talk about some detectors here. And in these lines, you will see this set of detectors here, some quad pole, some dual pole, a single pole one. I choose this one because they're also the one covered by the book that Irena showed in the last slides. So if you want to know more details about it, if you go to the book, you can read about it. So it's, it looked to me a nice, nice to show these things because then you can have a book to see more details about it. But before I continue, is there any question? So far, so far, so good. Very good. Let's proceed. Now, before we start, I would like to show you not the punchline, but the things we are dealing with. So this is an RGB with Pauli coordinates of an ALOS 1 image acquired in Japan, near Tokyo. I will talk more about this data set later, but before starting with all the maths and really kill the audience, I would like to show you what we want to end up doing after, so you can be waiting for what comes after. So the sea here, the blue part, it is blue in the image because it's a Pauli representation. The blue represents surfaces, and polarimetry is very nice in picking up that all this part here is a surface, so it's the sea. So it looks pretty nice for people also that are not familiar to radar, because they look at this and say, "Oh, it's blue, it's the sea." So then these objects inside the sea, over the sea, they are vessels. And you see the colors. This is green, red, yellow, light blue. Some is a light blue, but there is not much blue inside there. If you look at intensity, the intensity of this is certainly not higher than this, but you see it, isn't it? You look at the image, say, oh, there is something there because it's green. And that is the idea behind it. We want to develop some detector that instead of looking at how bright this is, how white these things look, want to look at the colors, say, sort of, how different it is polarimetrically between this one, which is blue, and this one, which is, oh, it's not blue, it's green. So that is the idea behind. So let's start with the maths now. So no, before that, there's still one that is not. So the one way that most of the quad pole detector deal with it is that they want to discriminate, as I said, between the surface scattering of the sea, of the clutter, what is called clutter. In detection theory, what you don't like is called clutter. Not that we refer sea as bad, clutter, but this is the jargon that we use. So don't be offended if you are somebody that look at the sea instead of the car target. It's just the way the detection theory works. The clutter is the sea, so the difference between the clutter and the target. And normally you use a local window where you extract information of the sea locally, and then to one of the test area where you want to see if there's a target there. There are other methodologies. This is possibly the most used, but there are others, like they look at larger area, they go for histograms and many other things. But this is possibly the one that is most common. So you have two windows, or sometimes even a third one, a ring window, that say, if it is close to the test, just reject. It's called a guard window. But anyway, the concept is the same. You want to detect, discriminate between the two things. So the first detector that was the quad-pole detector that possibly was proposed, it comes back to the 90s, is the entropy from the Clopot-Tier decomposition. You have seen that. So you take this matrix, you diagonalize the matrix, you look at the eigenvalues, and then you extract the entropy of that thing. What happens if we have, or let's say, what happens if you have a dominant target? The entropy is low or is high? Raise your hands if you think is high for dominant targets. Raise your hands if you think is low. Good. Dominant targets is low. So if you come back, if we go back to what we saw before, the ellipsoid, here it comes, the ellipsoid. So normally there are, Clopot-Tier tells you that there are normally 3 axes to these 3 eigenvalues if you have quad-pole. If you have a dominant one, you only have 1 eigenvalue. What does it mean? That your ellipsoid became a line. So if inside your space, you have just one single line, which is one single vector, all your polarimetric space is just one single vector sticking out, one line, that is a dominant target, and you have an entropy which is equal to 0. In reality, it's never like that. There is one which sticks out and many others around. So it's not really 0, it's about 0.01, whatever, 0.1, but there is always something there because there is noise. Thermal noise is uncorrelated, is everywhere. So anyway, if you have one single vector, then your entropy is very low. You have a line, your ellipsoid became a line, and you get a low entropy. The C, do you think is a high or a low entropy? Many people think it's a high entropy for the C, this distributed target. So a target of many pixels distributed, how many people think is a high entropy? How many people think it's a low entropy? Very good. I didn't manage to trick you. Distributed target can have very low entropy, can be single. It looks, what are you saying? It's many pixels, it's distributed, but it can still be single because it can be represented by basically a single scattering matrix, a single vector. So you look at the space with all the vectors sticking out, and they all go more or less in the same direction, the direction of the surface scattering. There is very little otherwise. So this one is this ellipsoid, which is like a line, has a low entropy, and the C is one of those. Each pixel of the C, you should see all the pixels, surface, 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 there are surfaces. So they have very low entropy. What about the ship? Will be high or low? People think it's high for the ship. People think it's low. The entropy is high because you have many, unless your ship is a single pixel. I should have said it depends, sorry. But unless there is only a single pixel, there are many pixels. When you put them together, one can be double bounce, the other can be dipole, the other can be helix. They're all different directions. When you form the ellipsoid, it doesn't go in one direction, it gets like an ellipsoid, it gets with 3 dimensions. When you go getting the entropy, for that you get a high entropy. So high entropy is, it's also written here. Next time I will put something on top. So anyway, they see low entropy, ship high entropy. That is the way. And it was proposed in the 90s already by Tutsi. So the second one I want to talk about is called the polarimetric match filter. This was developed by a god of polarimetry that not many people know. And I hope everybody knows. But anyway, it's Novak. The guy designed a lot of this detector, match filter, white filter, optimal detector. It was a lot in detection theory. So, but these things the theory that it was based on is very old. So it comes from the 60s, from Fisher. Although he proposed it in the 80s, but it's old stuff. So anyway, what we have here is a ratio, see, top, bottom, like that, a ratio, and on top we have a quadratic form for our target. So this is the power of our target on a projection vector omega, whatever. At the bottom denominator, we have the covariance matrix or coherency matrix for the C. So again, the power of the C at a certain scattering mechanisms, if you want. So if you optimize this ratio, you will get the maximum is the omega, is the projection vector, which produces the best return for the target, constrained to the smallest return from the C. So you maximize the contrast between the two. And so it is great, right? Because you get the image with the highest possible contrast between the C and the clutter locally, because you do these things locally with the train and test window that we saw before. So how do you do this? I leave it to you to have a look at this, but it's done with a Lagrange methodology, with the Lagrangians. You do these derivatives, and you end up with this equation here at the end. What is this equation? Anybody knows? Anybody wants to try? Yeah, this one. What is this equation? How do you solve this? Yeah, but how do you solve it? How do you find out the lambdas? Yeah, yes, you're getting there. It's a diagonalization. Yes, yes. You put this here, then you set it equal to 0, and you find the basis that diagonalize the matrix. So we need to diagonalize this matrix, and lambda here are the eigenvalues. This is Clopot-Hirsch. I don't know if you have ever seen this way, but if you put here just this, forget about this, just this, that is the diagonalization of TT. That's it. So it's all, it's the same stuff that we do over and over because it works. So that is diagonalized this matrix, you get the eigenvalues. The biggest eigenvalues produce you the image with the highest contrast between target and clutter. Any question? Go to the next. This is another detector proposed by Liu. I think this was around 2005. This is similar to another detector of Novak, very, very similar, which is the polarimetric whitening filter. But Liu with Vachon, the Canadian, they design it for ship detection. So if you do all the calculation there, go to the paper to see more information, but what you end up is with this final equation here, which looks like a quadratic form, is not, or sort of, because this is not normalized. This is your vector, your actual observable vector. It's not a projection vector. But what you have here, you have the covariance matrix of the C -1 inverted. So what you are doing here is that you create a matrix which spikes or is peaky where the covariance matrix of the C is missing. When you divide something, if you divide by 0, you go very high. If you divide by a big number, you go very small. So imagine that, and I need to leave this. Imagine that the C has this shape like that in your ellipsoid. When you invert that, so that is the vector for the C. When you invert that, what you get is something that will be inverse to that. So the matrix -1 will be this direction. So this is the C, this is inverse. So it will be the places where the C is small, that matrix will be big. So that matrix will stretch the vectors which are opposite, if you want, to the C. So when you multiply to your vector will be amplified if it's very different from the C. It will be reduced is very similar to the sea. So you produce an image which is filtered in a way that things different from the sea are enhanced. Different things that are equal to the sea, they are somehow abated, they are brought to one, they are normalized. So I hope that was clear, but you can also ask later. But it's the same concept. See, what is the sea? I want to go different to that. The fourth detector I'm showing is this one, the polarimetric notch filter. So this does again the same trick, but this time with the covariance matrix. So you get this partial scattering vector, which is vectorized in your covariance matrix, which is a 6-dimensional vector, because in the covariance matrix, there are 6 independent numbers, 3 diagonal, 3 off diagonal. The other 3 off diagonal are just the same, just complex conjugates, so you don't need them. So 6 vectors, and then you calculate this for the sea. So if your sea, the covariance matrix for your sea is this line, then what you get there is still a line. Still this vector there, still a line pointing in the direction where the sea is. So then what it does, it looks at the complementary space, the space that is orthogonal to this one. So if you have the line goes in this direction, you look at everything is inside there. A projection inside this thing that is perpendicular to the vector representing the sea. So you go for the complementary space, for what is different from. Everything is different from. Calculate the power inside this complementary space, then the total power minus power of the sea, which is this complementary space. If this is big, then means they have a target. If the sea takes you all the power, so the total power minus power of the sea is basically 0 because all the power is inside the sea, everything is inside the sea, then you don't get a detection. If you have something that sticks out from the sea as a projection in the complementary space, then you have that this thing is big and it goes above the threshold. And this is a coherence. There is more to it, but this is just the intuitive view of what is going on there. So any question about the quadpole detectors? That was the hardest bit. No, this one is easier, the dual pole. So let's go to the dual and single pole. One that was very used because you can use with Sentinel-1 SLC images is this one called reflection symmetry. So if you have a target with reflection symmetry, then this term here, the cross correlation between co and cross, will be basically 0. They will not have cross correlation. Now, have you heard about reflection symmetry before? Otherwise, I will explain it. So a reflection symmetry is where inside your resolution cell, the right part of the target is similar to the left part of the target. So this is reflection symmetric. This is not. This is it. It is. This is not reflection symmetric, yeah? Because what is on the left is different from what is on the right, especially if you see this way. So if inside your cell you have this symmetry, then you have this called reflection symmetry. What we normally do is not look at a single cell because they can be speckled, but we look at an area. So on average, your pixel should have the right part equal to the left part. If then this happens, then you have that your co-cross correlation is equal to 0. So it vanishes. The C12 term of your covariance matrix vanish when there is this reflection symmetry. The C, do you expect the C to have reflection symmetry? People say yes. People say no. The C has reflection symmetry normally. Because more or less it's a surface, so what is on the right is equal to what is on the left, in average. If you take a single pixel, no. But if you average, then more or less you have it. There are things like meteorological phenomena where this may not happen, but normally it is okay. It's a good approximation. While boats, ships, no, because the stern may be different from the bow. Oh, I don't know if the right words, but anyway, the front with the back can be different. So if you put a threshold on C12, then if you have a C, it will be very low. If you have a target, it will be very high, you get your detector. And finally, you can want to present this with a single channel. So just put in a threshold over a single channel. The best channel for doing your ship detection, it is normally the HV, the or the VH, the cross polarization. Normally, this is the best, unless you are going very shallow angles, so very shallow angles, so far away, big incidence angles. Yeah, it's shallow angles, yes. So you are going far away because that the sea doesn't scatter much. You have a lot of double bounce from the boat. So in that case, the HH is the best. But normally for the like Sentinel-1 type of acquisition, most of the image will benefit from using HV instead of HH, because HV, because of reflection symmetry, so there is not much cross pole coming from the HV. Okay, so, and then you want to have a way to set a threshold on these things here. And setting the threshold is the next things we will see. But are there any questions? No? So we can go. Setting the threshold. One way to normally do this is to use some statistical test. So you want to see the distribution of your target or clutter or your target and try to find out something. So it's a classical hypothesis testing. And when you normally do an hypothesis testing, you normally have two hypotheses. You will have a null hypothesis where there is only C clutter, and you will have an alternative hypothesis when there is your target is there. So then it boils down to setting, to have this hypothesis testing, as we have seen in statistics, like the Z-score or the t-test, all these kind of things, you know? The crucial bit is to understand what are the distribution there before you can set your test. And you can do that by looking at the PDF of this observable. For instance, this is the PDF of a certain observable gamma, whatever is your, it can be the match filter, it can be the reflection symmetry, the entropy, whatever is you would call it gamma, when you have only clutter. And you can calculate the probability of false alarm, which is the probability that you pass the threshold, but you have clutter. So it's the integral from the threshold to, well, this is a normalized one, but normally will be infinity of your PDF. And this is your probability of false alarm. Another way is to get a likelihood ratio test, where you on top, you have the PDF of your target, hypothesis 1, bottom the PDF of your clutter, hypothesis 0, and then you try to do things with that. So to set a threshold based on that. By far, the most used one is the CFAR, constant false alarm rate, which is based only on the probability of false alarm. This is because in most cases, we don't know the probability of the distribution of our target. We can model easily a surface because it's this type of like say distributed target with fully developed speckle, or even with texture, we can model it. But when it comes to boats, to ships, they're so different pixel per pixel that finding a statistical distribution is very challenging. Somebody tried, and Pasquale Iervolino, his detector is one possibly the state of the art at the moment, that using a likelihood ratio test. But most people, the vast majority, 99%, just use CFAR. So only false alarm without the one of the target. And we were over. So now it hopefully gets a little bit better, easier. So any question about this theoretical part when we talk about all these detectors and these things? Anything was not clear? If not, we can go to, here there is some example of applying this detector to see what happens when you try them. This is done with the image that I showed at the very start with ALOS-1 image from JAXA, so Japanese Space Agency. This was acquired in Tokyo Bay in 2008. This is how it looks with an RGB Pauli on it. And as we said, the sea is this area blue. The targets are of different colors. And at the time of the acquisition, a measuring campaign, a validation campaign was done. So they had a radar, ground radar, and also a camera up here, and they were looking down at the bay to see what was going on while ALOS was passing. And each one of these shapes was identified inside their video or their radar. And the green one is the one that you actually see inside the image. So you do see there is something there. The red one, most of them, you don't see anything there. So there is no signature inside the radar image. Now, either because the scattering was surface-like or because they were very weak, but we simply don't see them. So I don't think there is any hope to detect them. They are not there. I mean, you cannot see them. So these were all small wooden boats. So that's why maybe it's the reason why we don't see them at all. And there is something here as well, inside this green line here. And here comes the next question. So, where it is? Yeah, what is inside the green line? So what you have to do here is to write words, write words about what you think is inside. So if you think it's boats, you write boats, vessels, vessels. If you want to write things that is two words, put an hash in between, otherwise we split the word. If you say, I don't know, sea monster, it will go sea and monster. Put an hash in between. So you can start, and then hopefully this will start. High electric power system. Okay. Any other bet? Show again. This bit here. What do you think is there? You see, there is also a bit here. Okay, coming, aquaculture, oil, seaweed, solar panels, windmills, farm. What is that? Yeah. I think, yes, I think everybody answered aquaculture. You are correct. It is aquaculture platforms. They grow seaweed that they use for sushi, the type of lever, I think it's called. And yeah, so that is correct. They are aquaculture. 1 second that I come back to that. Or this one. So you see, they are little platforms. The resolution of ALOS-1 was not the best, was quite large. It thinks probably 20 meters or something, but still you see them. And how you see them? Because they are different color. They're a little bit red. There is a little bit of double bounce going on there, maybe even a bit of, in this case, volume scattering, or anyway, that oriented double bounce, which is different from the sea. So by this characteristic, we were able to see them. If we were just looking at intensity, no way you could see them, as you will see later. So we tried then the different detectors, and I don't want to read all the numbers, all the parameters, but you find this inside the book. So if you read the book, that Irena was showing in the last slide. There is a chapter that explains all the data, the parameters. There should also be the code for that. Otherwise, you can ask. And so you see, this is parametric notch filter. We do detect some of this aquaculture, not all of them. We do detect most of these boats there that they were indicating. Then the polarimetry match filters works very well for the aquaculture. You see, you detect more of them. Is missing. Oh, this is a false alarm. And I think it's going well as well. One false alarm, yeah. Also, I say false alarm question mark because it's far from the things. Maybe they didn't see it. Maybe it was something there. Then this is the Liu detector. You see this one struggle a little bit with aquaculture, but is good with the other one. Detects all of them. Maybe a false alarm. And finally, the entropy is super good for the aquaculture. It detects all of them, possibly all of them. But I think it did struggle a little bit with missing targets. So, but it was very good for this. And now there is probably a lesson learning here, that the detector that seems to work the best for aquaculture were possibly the entropy and the PMF. So this one tried to maximize the different, look at how many scattering mechanisms you have, and also to maximize the difference between target and clutter. So while the one that works on intensity, like the Liu, because the Liu at the end, it does work on intensity because that thing is like an intensity type detector, miss them because they're not very bright. And also if we go to the symmetry detector, which is based on intensity somehow, you miss all of them basically. And the same is with HV. If you just look at their intensity, you just don't see them. So only by looking at difference in colors, you can tell that things are there. But if you go at intensity type of things, how bright they are, then you don't see them. They're not that bright. With no offense. So here is a comparison between quad pole and dual pole, and you see that the quad pole worked better in this scenario, mostly because you have quite weak targets. I don't want to say to sell smoke. If you go for very big container ships, you don't need quad pole. You just see them from space, maybe from the ISS. You see them. They're huge. They're enormous. They're very easy in any way. But if you go for the smaller one, like the fishing vessels, so things that are less than say 50 meters wide, long, or 30 meters even, then you need a little bit extra help. And the color, the polarimetry can be what is helping you detecting them. Okay, here you can see the relative operating characteristic, receiving operating characteristic curve. So the draw curve that shows probability of false alarm against probability of detection. You can see more on the paper, but again, it shows that the quad pole detector that are the one that end up the best for this kind of exercise. So quad pole help when you have the challenging scenarios, or seems to help so far, as looked like helps when you have these challenging scenarios. Any question regarding maritime application? Otherwise, we go to the second part. Yep. If you use the entropy, no, because the entropy, they're both very high. If you use other detectors, yes. The parametric match filter will not really show your oil spill, because then it's looking at differences between the train and the test. If you are inside oil spill, train and test are the same. You wouldn't see it. So it depends on the algorithm that you use. But you can absolutely do it, but you need to use the right algorithm. And one thing that you may also want to do is to have some information about the spatial characteristic of the target. So the oil spills are often like filaments, while these things are point-like. So if you also add that type of information, then you improve even further. But oil spill, there is a lot with quad pole that we have done in the past 10 years, maybe 10, 20 years, have a look at the book. There is a couple of sections on that as well, on oil spills. I think you already know, actually. Anyway. Any other questions? So we go to the second part. So this is about change detection. I think you have seen the use of multiple images by doing interferometry. What I want to show you is how to use these multiple images, but in a different way, not looking at the interferometric phase, but just looking at the covariance matrices, but looking at the shapes of these ellipsoids in the space. And there are many applications for that. Here I want you to find a scene where you can have many of them. You can have agriculture, urban, and I think this area floods too. So I say it looks appropriate for what I want to talk about. And my example here is about flooding, which is a very important thing. This is very also currently we have seen how devastating flooding can be. Here there is some stats you can read, a little bit old, a little bit partisan because it's UK, but you see the numbers here are big. The losses are huge. And yeah, here say why you want a cell pitch for remote sensing and floods, why you want to use them. I'll leave to read this to your leisure. And I would like to go to the physics bit. So how do we expect floods to look in such images? Now, you have seen that what we have said before, that water is quite impenetrable. So the electric constant very high. So it calls for surface scattering. There is no volume scattering in water with this microwave that we use. So now if the water is smooth, then you will have, that is like a mirror. So everything we send down bounce off. An experiment that everybody has done in their life. If you go to look at a mirror, not straight on, normal, but at a slant, do you see yourself in the mirror? I hope everybody say no, because you see what is there. So I see you guys if a mirror is there. I don't see me. I have to go there to see myself. This is why radar cannot see any reflection from this smooth surface, like mirror-like surfaces, because we send there and it's not coming back to us, it's going away, it's going specular. However, if you have some roughness on top of it, then things start changing. So you can imagine roughness has a lot of facets, like small surfaces on top of this surface. And some of these surfaces you can imagine they will face you. Some not, some yes. The more rough it is, the more facets will be looking at you. This is an intuitive way to understand how the more roughness you have, the more likely you are that something is coming back to you. And the example that I can think about here is a disco ball. If you look at a disco ball and there's only one light, you see an area which is bright and the rest not much, because those facets are straight looking at you. There is some light that is shining there and is going in our eyes. And it's a little bit like that. So the surface creates this roughness, creates these facets, and some are looking at us, but it's not exactly the same. So don't try to model this physically, because here in the disco ball, one of these tiles is many order of magnitude bigger than the wavelength. In the roughness on the ground, one of these tiles is smaller than the wavelength. So you cannot model it this way. It's just a way for you intuitive, for you try to remember what is going on and try to get it inside your head. But you cannot use this as a good physical analogy. It's just a funny analogy for you to remember. So please don't quote me when he says it is a disco ball, but use it for like the same for the spaceship, but use it for remembering. Use it for remembering. So floods look dark because they are smooth normally. And here is an example, a bit outdated, 2002. Here is another example, even older, old school, 94, where you can see these floods look dark inside images. And this is next question to you. So are there situations when these floods, this one, are not dark? Can you think about some situation when the floods will not look as a dark patch, but it will look bright? Why? When this can happen? Or it's never happening. If it's never happening, don't write it. But it does happen, I tell you. It's a spoiler alert. So why? Sometimes they're not dark. Let's see the response. The breeze, yes, very good. Under forest, very good. What is done? Muddy water, no, this is not good. In urban areas, exactly, very good. Some answer are split, I think. Strong winds, very good. Wind and the breeze, I think these two seems to be the winners, wind and the breeze. Absolutely right. If you have stuff on top of the water that floats around, then you have a very strong return. We recently saw that also plastic in big accumulations, they can have a strong return. This was it's a recent paper, ask me later if you want, that was done this in the Balkan regions. So wind is another thing. If it's very windy, you will see ripples on top of the water. So you also in ponds, when it's very windy, you see the ripples on top. These are what are called capillary waves, and they're very, they produce a lot of backscattering. So the water can be bright because of these capillary waves. Things inside the water, under the water, generally don't impact because you don't see them. They are deep inside. And another thing that was cool here, if you have under vegetation, then your backscatter is not expected to go down. If you look, for instance, at rice fields, when you flood the field, there is water there, it's flooded, but the backscattering goes up because of double bounce. So it's tricky that if you have vegetation, of course, if you have an urban area, the backscattering will go up. Very good. No, this one. This one. Okay, so how do you want to detect floods? Just skip this one. Detecting with change detection, so using two images. And so what is doing change detection? So you have one image, another image, and I'm sure most of you have played the game Spot the Difference, where you have to see in two cartoons, so you have to see what is different, what is missing, the color are different, these kind of things. So it is basically spot the difference when you look at two images, and then you have to say, what is the difference between this and that? And I hope you can appreciate. I wanted to make a question, which one do you prefer? But I said, maybe it's too much. But anyway, you can understand which one I prefer, being born quite a while ago. So, what is the idea here? You go on the scene once with your satellite, say Sentinel-1. You go on the scene after 6 days, 12 days, depends where you are, depends how many Sentinel-1 we have in space. And then we create this stack of images which go through clouds. So this is one of the advantages doing change detection with SAR and now with optical, that we don't care about clouds. So we can just get an image every time, almost every time we go, while this is quite important for change detection, for assessing flood risk, for instance. So we do things with the International Disaster Charter, where when there is a flood in Scotland, we get images one after the other. So you can get 12 images in 3 days, and then each one of them is good, and you can use them. So the idea about using these two images is then combine them in a way that makes sense. The easiest things is to just use one polarization channel. You select the one you want, say HV, for instance, or VV, and then you use that one. How you combine them? Now, in number theory, our civilization is based on plus and minus, on plus and multiplication, addition and multiplication. This is possibly the way that we see the world, and this is also the way that we can do that. You can either have a minus, or you can have a ratio there. So it is what number theories teach us. So these are the simplest way of creating change the differences between acquisitions. And my play again is to you to find out different ways. I don't think there are, but anyway, if you are good at maths, try to find something different. So minus or ratio, these are generally the way we do it. Or you can normalize it. So you can have normalized differences, like people in optics use a lot with their indexes. You can also do here. So don't think I have time for that, but anyway, it tells you why you may want to normalize. Is scale important or not? So because the difference you see is if you multiply one of the images or both of the images by a thing, the difference goes up, while the ratio doesn't, because you divide it. Again, it would be nice to show here, but you can imagine how this, you can see how these things is scale invariant. If you have a calibration error on your images, and each of your images is multiplied by 1 billion, because some evil gremlin did that, when you put it there, it goes away. If you put it here, your difference will also be scaled on 1 billion. You will not be able to do it. So scale invariant or scale invariant, you can read more about that. The advantages and disadvantages of using these things. Co-registration, you have heard this before when you do interferometry. I don't have to explain what it is. I just want to tell you, do it. If you just ask, say, Snap to stack your images with geocoded images, it won't work. Often you have 1-2 pixels of shift between the images. They will see differences everywhere just because they're not well aligned. So do co-registration. It doesn't have to be as good as the one you do for interferometry, but you still need to do it. Otherwise you have noise everywhere because of these little shifts that you can have between images. Okay. So any questions so far? So now we started the mathematical bit. So we can divide this detector between the physically based and the statistically based. I will start with the physically based. If you want to develop something that is has physics inside, you need a model. Model is the thing that you, otherwise it's very hard to do physics without any model. When you talk about changes, you need to have a model for what you mean with change. So what is a change for you? How can you characterize a change? And again, coming back on the fact that we use plus and multiplication in our maths, the first model is the additive one. So you have nothing there, and then you have something there. Or the opposite, you have something there and then nothing there. So that could be a tree that has been chopped, a building that tear down, a building that has been built, but something that has been added to the scene. You have something and then you have something plus something else. And once you have that, you can say, okay, so what if I see the difference between covariance matrices? So this tells me the partial target at time 2. This tells me the partial target at time 1. If I do the difference, I get a change matrix, which is not anymore one target, is the differences between the targets. Then what I do an optimization. So I do the quadratic form as usual, because I want to see the power for each scattering mechanisms. I want to see the scattering mechanisms that changed. So I look at the change matrix and I do the quadratic form, which is what it's doing here. And then I do the classic story of the optimization with the Lagrangian, you know by heart. And this is where we end up with this diagonalization of this matrix here, which is the same diagonalization of the PMF, the match filter, is the same diagonalization of the Clopot here. The only thing different is what you put inside. So the search space where you look. And why they are all the same? Because this is a convex problem. These matrices are Hermitian, and there is no better way to deal with them than using some linear algebra type of processing, because you know they're very fast, and you know they're so linear, and they're all convex and Hermitian. So there is nothing better than this, really, to extract the axis of your ellipsoid. It's always coming back to these things that they look like ellipsoids, and then you have to find out the axis. With a change matrix, you have a little twist that the matrix can be negative. So it's not the ellipsoid can be sucked in like in a negative space. No, you cannot imagine it. There's no way I think anybody can imagine that, but can be negative as well. That is the weird things, but it still is convex. Still you can do it, but it's not as clear logically as the Clopottier, which is an ellipsoid, and you find the axis. Okay, so that is the diagonalization of that. Second model is the multiplicative one. So not a plus, but a times, a multiplication. So this happens when you have a transformation. So you have a target at the start, and this target transforms into something different. The easiest, the most logical, and the clearest transformation you can think about is a rotation. So T2 is rotation of T1. T1 after you rotate it, after you take the ellipsoid and you rotate it. So that is possibly the easiest that you can think about it. But I want to pick your creativity here, and I want to see if any of you can come with a different way of seeing this thing. So back here. Which applications would you use a multiplicative model? So rotation is one. What else? What is this transformation? What can happen that can transform a target from something to something else? This is tough, don't worry. Try something, but it's okay if we'll talk about it. Okay, we have 5 brave people. Let's see. So landslide, displacement, crop growing, some is being cut, vegetation growth, moisture. Very good. Well, some is being cut, is hard to see. But anyway, landslides. Possibly, although landslides often they add stuff. So you have the mountain is here, then the mountain is not there anymore, but it's here. So the rocks, not the mountain, sorry, the rocks are here, the rocks are here. So here seen with no rocks, with rocks, no rocks, no rocks to rocks. So it's more an additive one. Although it's tricky. Moisture, that's a good one. But the thing is often moisture is, I think it's okay, because also it changes the other eigenvalues. If you have something that's just changing your first eigenvalue, like wind for the sea, you have very calm surface scattering, very bright surface scattering, then that is additive. You are adding surface scattering. With moisture, you also have the second eigenvalue get bigger. So it is indeed a possibility, moisture. Defoliation. Yes, I think so. It's complicated, but maybe yes. Because yeah, first you see the volume. No, maybe not, because you see the volume, and then you don't see the volume, you see the ground, you see the double bounce. So maybe that is still additive. So anyway, what I wanted to come here is that it is hard to think about multiplicative changes, transformations. Normally, we are used to see additive changes or to understand additive changes. But there are situations, like most of you said, like the rotations, where this is important. And when this happens, you should not use an additive model, you should use a multiplicative one. Otherwise, you will make mistakes in interpretation. Okay. So, Magda, I think it's 12, right? Until 12. Cool. So with multiplicative model, oh, what do we have here? Oh, surprise, surprise. What is that? It's the match filter. It's back. So again, on top, we have the first target. On the bottom, we have the second partial target. So numerator, denominator. And then we are looking at the ratio between the two, looking for the projection vector, the omega, that is producing the biggest difference between the two. And you can, well, if you read this paper here, you can see how this converts to a transformation model, because it's a transformation between the two matrices that you have here. But if you read the paper, it explains, I don't want to go, you can ask, but I don't want to bother too much at this point. So, but this is a transformation model looking at this ratio. And also, you know, the inverse of a multiplication is a ratio. And so this is what we are doing here. And then you do again Lagrangian, you get the same optimization that we were getting with Novak in the 80s and with Fisher in the 60s, which is diagonalized in this matrix here. These are Hermitian matrix, each one of them. Their product is not Hermitian, but still has real positive eigenvalues, and you can read the demonstration inside the paper as well. So if we can do it, there will not be monster coming out of this operation, but it is not Hermitian. So when you do it, the exercise that you do this afternoon, you will be doing it in Python, and you will see we use a different function for optimizing this, which is not Hermitian, than what we use for optimizing the other one, the difference, which is Hermitian, because it's the sum of, it's not semi-positive definite, because it's the sum of Hermitian matrices. So I don't want to overwhelm you at this point, just to say this maths can be done. It's not, it's all proven, you can read it. So again, difference, additive, multiplicative, it depends a little bit what you're doing, and you really have to make sure that you know which model you should use. So let's look at some results. This again, L-band quad pole, ALOS-1, acquired by JAXA. This was acquired in England, in Morecambe Bay, which is close to the Scottish border, a bit south of that, Lancaster. So first image, second image, RGB. You see the C is blue again, E works. Then here, this agricultural field became green. There was some growth there between April and May, so 1.5 month distance. So this is the image, how it looks. These are all mud flats. So it's very tidal, so like 7 meter difference of tides. So we apply first the additive model, and this image this is the maximum eigenvalue represented using Pauli basis. So you take the eigenvalue, which is a vector, then you plot in an RGB using the Pauli convention, and then this is what comes out. So sorry, eigenvalue and eigenvector. Eigenvalue is a number. The eigenvector is the one that has the 3 components. So you see there is an increase in blue scattering on this area here. You look at the images, and indeed this is bluer than that. There is more surface scattering. So we were able to pick up this increase in surface scattering due to extra wind. So that's why I say it's good to use an additive model there, because the wind is increasing the waves, so the surface scattering. There is green, I hope you can see here, which is related to this green that is coming here. So there is more volume scattering due to the crops. And there is quite a lot of red dots here. What is this thing? This is a caravan park here. So what happened? So it's a holiday location. Although you say, oh, you want to go to holiday there, but indeed it's a holiday location. It's also beautiful, but it's not the kind of beach holiday you can expect from the south. So you see, there is a lot of reds here, which are the caravan that went there in the second image, and a lot of reds here, which are the caravan that were not there in the first image, but so not there in the second image, but they were there in the first image. So these are, you see where the things moved around. Here is what appeared in the second, here is what appeared in the first, but not in the second. So you do see the movement of the caravans around, which produce double bounces. So these dihedral, horizontal dihedrals. Now, we try this with the other one, the multiplicative, and you see the color all over the place. So there's green on the sea, there is blue on the vegetation part. This is because these one are projection vectors, they're not scattering mechanisms. These are vectors that allow you to do transformation. So it tells you this is the first ellipsoid, this is the second, go in this direction to move it. So it tells you where you have to go. But this thing is not what you have after or what you have at the start. It's just how you to transform. So don't read them as scattering mechanisms, but just as projection vectors. But the power of this is even better. So if you look at this area here, is brighter than what you got before. So if you just do detection, this is quite good. But if you want to interpret, then it's not the best. So then we have the statistically based. Do I need to close quick? Do I have other, say, 5-10 minutes? Okay, so these are the statistically based. When you want to do that, you need again to come with some hypotheses. The first hypothesis is that the first target is equal to the second. The second is that there is a change between the first and the second image. Be careful, the sigma is for the expected value. So it's the covariance matrix after you sample an infinite number of bins of pixels. So while what you get from the image is actually this one, the C1, is the sample covariance matrix. So when you apply these things, statistical tests, you have to keep this in mind. Some is ideal, the underlying statistics, something is real, so what you estimate from the data. So simplest one uses the Wishart distribution. Have you heard about Wishart? Yes, no? Yes. So I can skip. So this is the PDF that I'm sure you have a tattoo of that somewhere or you remember perfectly. So we can skip. No, so anyway, the one very famous detector was this one proposed by Konrad Sen in the early 2000s. And so what it does, he assumes that it looks at differences between the C1 distribution of the first target, and the one of C1 plus C2 divided by 2. Now, if C2 is equal to C1, C1 plus C2 divided by 2 is equal to C1, 2, no? Because they are the same. If they're the same. But if they're different, then you have a difference there. So why does this trick of having C1 plus C2 instead of just having C2? Because it makes the maths easier. So it's easier to do the maths, but they do the same job. It's just that it makes easier the maths. And what you come up with is this equation here, where NM is the number of looks, P the number of polarization, and that is the determinant. Some people use different symbols too for that. So one thing that is common is because it's very hard to estimate N and M, the equivalent number of looks, people just look at these things here. So the product of the determinant divided by their sum, and they use this as their detector. So they remove the scale, which makes it not a straightforward test, but it still tests the same stuff. So this is what you will see inside the Python code this afternoon. So we don't bother estimating these things, which are very complicated to estimate, and we just go with this bit here. If you want to know more about how to estimate these things, you can read Stian Alfinsen about estimating equivalent number of looks. The second one, the famous, is the Hotelling-Lovelace trace. Why it is the trace of this matrix here? Why it is famous? Because we know the distribution, so we can set a statistical test on that, as we were saying before, using what we were talking before about the CFAR is the same stuff here. So now, look at these things. What does this remind you? It is again the same. It's the PMF. It is the multiplicative model. It is again the product of 2 T2 minus 1 T1. It's the same thing again. It's the same product. So before we were using for the optimization. Now we are considering the trace of that. So what is going on here? Are these two detectors the same? Not exactly. What they're doing, they're looking at the same search space. The search space is this one. And in one case, we do an optimization to find where this ellipsoid is sticking out the most, to see the one that optimizes the contrast. Here, we are looking at what is the average surface over this ellipsoid. So we are doing, you can see that the trace is also equal to the integral when you average overall the quadratic form, and you can read more in this paper here. So by doing the trace, we're doing the integral, we're doing the average. So we are looking at the average inside the search space. By doing the optimization, we are looking at things that are sticking out. So it's the same stuff, but they look at different properties of this search space. So, and I like also to close it here because we go full circle on the ellipsoid, on the spaceship. And so it's a nice place to close it. I think we have no time for going through this, but I leave this as to you to think about and maybe come out and we chat about it. The first things I would like to know from you, what you believe is the hardest concept here. And it's a pity we cannot do because you can also vote. Maybe we can start and then we turn off quickly. And the second things, I would like you, if you have any question, if there is anything you will like more explanation about. So do we have 2 minutes to do this funny thing? Let's do it. So. Okay, so now you should find something that say what is the hardest concept you have learned. And once you write it, everybody will be able to see it. So be careful what you write. And you can also rank it. You will see what other people say. And you can say thumbs up, thumbs down. If you think it was really hard, thumbs up. If you think, no, that was the easy bit, thumbs down. Let's see if it works. Please don't say understand his accent. We have an entry for multiplicative models. They're tough indeed. Everything. Oh. Multiplicative seems to be the hardest. The algorithms, yeah. But in general, can I? No. It's going up, yeah? Mm-hmm. Yeah. No, that is quite tough. I like you to show that to you so that you know what is going on, and also you can implement it. So there is the final equation there. You don't have to dig inside the paper, but they are hard. I understand. That's why I try to make you to see them in a geometrical perspective, this ellipsoid in spaces. Maybe it's easier to see them. Okay, so let's say the multiplicative models are by far the hardest, it seems, and math in general were tough. Very good. So now you have more questions than you came in. Shall we go to the second one? But I think it's connected to this as well. So, and also probably we can talk about this outside. This is just a way to gather questions, people that, if there is common questions, then I could talk about it. But if it's, I don't know if we have time for answering question now. It is okay? Okay, so your chance to write your question and people can vote on your question. Oh, yeah. Yeah, yeah. Mm-hmm. Yeah. Yeah, yeah. Mm-hmm. Yeah. Mm-hmm. Yeah. Okay. Yeah. It generally is consistency. Writing, so it depends on which type of detector you're using. If you take just a channel and then you do a threshold on that, then the only thing you really need to do is consistency. If you go linear, they will have some distribution, say a rayleigh or whatever, or exponential if it's your intensity. If it's the log one, they will have a log norm distribution, normal distribution, or something different. So the important that when you stick to that, then you use the right distribution for setting the threshold, and you don't mix it. When you want to apply those detectors that look at the optimizations, that has to be linear, because this is all linear algebra. You don't want to shuffle dB inside there. I don't know how you would shuffle dB inside there, but it will make things complicated. So yeah. So if it is an optimization, stick to linear normally. If you want to go log, it's okay, but use the right distribution. Don't mix and match. What happened to the alien? Very good question. I don't know. You have to answer that one. How to apply models to application side like landslide and moisture change detection. Yeah. This is a big question. So you're interested how to do change detection for moisture, right? Yeah, I don't have a direct answer. What I can say is that normally people, what they do to extract soil moisture, or one of the trends to extract soil moisture, is don't look at absolute value of soil moisture, but to look at its changes, its relative value. So there is an initial normalization that people try to connect to a value of moisture, and then look at the changes to say it is moister than before, it is less moist than before, and maybe you cannot get the absolute value, but you know the changes of that. It really depends on your application. It's hard to answer this question, but if you want to have a chat, we can discuss it later. Change detection with Sentinel-1. Absolutely, you can do it. It's all you saw here, almost all you saw here, can be applied to Sentinel-1. Sentinel-1, you have dual pole. You have to make sure you get the SLC, don't get the GRD, so you have the phase. But then this means that your covariance matrix is two-dimensional, 2 by 2, it's not 3 by 3. But all the algorithm can apply, all of them. You can do the difference between the two C matrix. I can suggest you a paper where we do earthquake monitoring with that. Or you can do this ratio as well. I think I can suggest another paper where people did something similar, for plastic, for instance. What else? The Wishart is very common to do that. So you see the two covariance matrices and then you compare. So anything you have seen can be done with single one, a little bit worse because it's not quadpole, but it can be done with Sentinel-1. How to integrate optical images? A good question. The things that at the moment, this is actually you guys should try to answer this question. It's very complicated. So there is not really much at the moment. So when you try to combine these two data, because they are so different, they are completely uncorrelated, there is not really a framework where you can say we create the covariance matrix of these things, and so it doesn't really work well. So most people, what they do, they use some black box methodology. Random forest is a feature, one of the elements of your feature vector or neural networks. So they use like, they consider as independent measurements, as you will combine wind speed with the SAR image, or they're completely different. I don't know if there is a way to do this in a better way because they are completely uncorrelated. But this is for you guys. Try to find a better way, please. So my suggestion at this point is to use a machine learning type of approach. Yes, no? Yeah. Yeah, I think the one on Snap, you just use a single channel. The one on Pulsar Pro, use the covariance matrix. So, Pulsar Pro is also an algorithm for doing ship detection. And this is the one also described in the book of Irena showed. And that one use quad pole if you have, or dual pole. One is Snap, I believe, is just setting a threshold. It's like an Otsu type thing, setting a threshold on the backscattering. Yes, how to set threshold, that's a good thing. You can have a look at the slides, let's say, by using finding a PDF and then try to set a threshold on that based on a constant false alarm rate. There are other ways that they use histograms, so you try to separate the histogram of the clutter, the histogram of the target, and you set it there. So a little bit more global approaches. But yeah, you need to find out which one works the best for your case. If you have a more specific question, we can chat about this later. Best detector soil moisture. Have a look at what ESA is doing with the Copernicus surface soil moisture product. There is a Copernicus product, 1 kilometer grid, where they do soil moisture and they use this kind of algorithm. Now you may argue C-band is not good for that, but the algorithm is still there. So you can have a look at the algorithm and you may implement. It's very easy to implement. It's just simple change detection. It's nothing too fancy. Can you incorporate more than 2 acquisitions to the statistical change detection? Yes, you can. You can have more than 2 acquisitions. Conradsen has a paper on that, where you look at a stack of different covariance matrices, and then you look at them as a stack. And if it triggers a change, then you take a sub area and you look if it still trigger a change, and then you know when the change happened in the stack. But yeah, definitely, or you can, all this one, you can apply recursively one after the other. So image by image, and then you stack the images together. Another one that I like a lot, I didn't present today, is the cumulative sums. So you can calculate the cumulative sums. If you don't know what it is, I will tell you later. And then this is really integrating all the information you have until that date. There are other ways even more complicated for doing that, but yeah. I think it's time, right? No, okay. Let's go up. There's something here. No, okay, it's all good. DCFAR detector intuition. So an explanation about what how the CFAR works. So it would be nice to have a pen here, but what you can imagine is that you have a distribution for your clutter. So this is the intensity of the clutter, number of times. This is your histogram, and this is what your clutter does. This is what you expected. Then you know that if you set a threshold here, the amount of PDF of histogram that you will have here of your clutter is very little. So you set the threshold where the amount left of your histogram is equal to or smaller than a set probability of false alarm. You say 10 minus 4, and you set it so that what is left, the area under what is left, is 10 minus 4. This means that the probability that you get a false alarm inside that scene set in this threshold is 1 over 10,000 pixels. Do you think it's a good number, 1 over 10,000 pixels? What about you have 10 million pixels to work with? There's quite a lot of ships coming up. So it's not very good. You go even smaller than that. It looks crazy. 1 over 10,000, but no, for ship detection is not good. What people normally do, they use of morphological filter after for refining it, because this normally comes a single point. You see, it's a single point I reject. So I don't detect ships smaller than 20 meters, but I remove the false alarm this way. So there are compromises, but yeah. Any other question people would like to ask? Yeah, please. Yeah. Yeah. Yeah, thanks. Absolutely, yes. Also, if you are looking for a good review of these soil moistures, one from Brian Barrett. He also does the quad poll. So I don't know if Irene is still here, but she worked a lot on soil moisture. You can use anisotrope, you can do a lot of things. And also Thomas Jaktuber after her. So there is many things going on. But this review is quite well. It's a bit outdated, 2008, I think. No, 2010. But yeah, no, there is a lot there. Mm-hmm. More questions? No? If not, oh, yeah, please. Yeah.
So we could use all these methods, or some of them more combination, or some neural networks. What is your perception of the future?
So you may have noticed an avid sci-fi reader. I love sci-fi, and I do believe that in 100 years or so, we will not be the most intelligent race on this planet. Everything is going there. At some point, we will need to give the key of the car to the machine, and we just sit there and hope for the best. But they at the moment, in the next few decades, I think it's a combination of the two. I think possibly, say, 30 years, it will be mostly machine learning, but also the machine will be able to create models themselves. But in 30 years. Now, I think it's a combination. Now, the things that I would not suggest to do is to chuck your data in and then see what happens, what comes out. Because you can really improve a lot by just asking the right question, by phrasing the question the right way. So by applying these things as pre-processing methodologies, and by trying to find all this observable, and then feed this to the machine, I think is a better way than giving the machine this three-dimensional complex data and hope for the best what it comes out. But things will change. They're getting more and more powerful. So yeah, at some point they will be able to do that either. They will be able to find out the equation themselves. You know, yeah. So I would suggest you to still have a layer of this before you chuck everything inside a neural network. Yeah. More questions? Very good. So